Share screen, wait for it. Okay, so first meeting, we learned that for Boolean logic, for our Boolean algebra, it can be associative. And we also learned it can be commutative. And we can learn
Boolean algebra.
commutative. And so those were the three we learned about. And let's look at what each of these are. Okay, so for commutative, it can go either way. So it can like be x multiplied by y equals y times x. Same thing right there. It can also be like x plus y equals y plus x. Same way, same order, as long as it's commutative, you can do it any way you want. And then associative is they have to be the same exact type, like it has to be either all multiplication or all addition. So
okay, so multiplication.
So it's like y times z equals x times y and then times z, or x plus y plus z. It can be the same as when you group together x plus y plus z. And so it has to be the same type. That's just for associative. It has to be same type of operation. It has to be either multiplication or addition. And then for distributive, that's if we have x, let's say, times y plus z is equal to, basically, if you distribute that out, xy plus xe. So x times y plus x times z. So those are the three properties we need to know about Boolean algebra. And
okay, distributive. Okay.
For the theorems, we have theorems. I'm going to go through. X multiplied by 0 is going to be 0 because this is basically an AND gate if we think about it. If we have x here and we have 0 here, both have to be true. So since one of them is 0, this is going to be 0. Because it doesn't matter whatever x is, because one of them is 0, the output has to be 0. Okay. Our next one would be if we had x multiplied by 1, that's going to be dependent on x. Since if we look at this AND gate again, let's just clear this one right here. And
okay.
If we had instead here, I'm just going to put it in a different color. Oh, oops, I'm still on the eraser button. Okay, if I had a different color here, if I had 1 here, and let's say 1 and x, the result, it's going to be dependent if x is 1 because we don't know. And so it would be dependent on x here. So if x is 0, that's going to cause this to be 0.
Okay.
But if x is 1, it's going to be 1 because both 1.
Both are 1. Okay.
And next we have x plus 0 is going to be dependent on x, and then x plus 1 is going to be
1 instead.
1. And this is an OR gate. So if we think about it for this one here, if we have x or 0, what's going to happen is 0 is going to be false, but it's an OR gate. So it's either one has to be true. So if x is true, it will be true. But if x is false, then it's going to be false because both would be false. Here, if we have x and 1 and we have an OR gate, and if this one is true, we can tell, but this one, we don't know if it's 0 or 1. And so because this one's true and it's an OR gate, it just depends on one of the inputs. So it's going to be 1.
Okay, so then x.
Okay, then our next one is x multiplied by x. So, and then x multiplied by x equals 0. And this one has a naught over it. So what this does is this is an AND gate with x and x here. So we have x, and x ANDed with x. That's going to be, if we look at that, X ANDed with X, the result, if X is 1, then this would be 1, 1, and that would make it true. So it's dependent upon the value of X. Because we can just think about this as really just a gate, an AND gate, where it's the same input for both. And so it's X and X. And so it's dependent. If X is 1, then both the inputs would be 1. And so then this would be 1. But if it's X and X naught, what's going to happen here is when we have X naught here and X here, X naught would be the opposite. So it'd be like 0, 1. So it's never going to be the same. If X is 1, this one's going to be 0. If X is 0, this is going to be 1 because it's the opposite. So then it would be 0, always the output. Okay. Now that we discussed a little about those, let's get into the actual fourth theorem. Okay, I'm just going to leave that up there. So let's get into the fourth theorem here. So I'm going to make this, if we have X and X bar, that'd be 0.
0, and then, okay.
The fourth one here would be X plus X would equal X and X plus X naught. So X plus X naught equals 1. And for X naught, we're going to get right here. So if we have an OR gate, let's think about this. And the input's X, same for both inputs, same variable. So it's connected. I like to draw it sort of like this because it's just dependent on that one. And then the output is going to be X because if X is 1, then it would be true. But if X is 0, it would be false because it's an OR gate. But if we have here for OR gate, if we have X and X naught, and X can either be 0 or 1, we know one of them will be 1. So our OR gate would be true then.
Oh, true.
Okay. Then another one we have is X plus X naught times Y. And so for this one, what we do is, in order to think about it, you can draw it out. So you can have your X here, then that's ORed with the multiplication of these two. So let's see, X naught and Y. And so that would be an AND gate between these two. And then it would go through here and an OR gate. And it's going to be equal to, it says here, X plus Y. And if we think about that, we go through here and we're like, how does that cancel in this situation? This X bar gets removed. Well, if we had X, let's think if X was 0 here. Oops, let me draw it out. If X was 0 in this case, so let's just put a 0 here, then this would be 1 because it's the opposite. And so then it'd be dependent on Y here. So we'd have a 0 and Y. And so the output would be dependent on Y. But if we had a 1 for X here, the 1 would cause this one to be 0, and this would be, our other one would be Y, so it's an AND gate, so this would be 0. So 1 ORed with 0 would be 1, and so then it could also be X. And so our output's either going to be X or Y, so that's how we get this. If we plug in 1 or we plug in 0 for X, it gives us this X or Y as our output. And then our next one, the final theorem you need to know, is just distributive. So this one's the nice one. So it's X times X naught plus Y naught, plus Y. And so when I draw that out, it has a naught. Let me put that in different colors so it matches. So when I do that, when you multiply that out, it should give you for yours X times Y. And if we look at that and we're thinking, how does that give us that? Let's do X times X naught. And when we do X times X naught, I'm going to distribute this down here. So I'm going to show you. So x times x naught, and I'll put a bar over this one, plus x times y. If we think about that, okay, let me draw the little bar symbol over this one, because we just went and we distributed, and then we distributed here. And when we did that, we got this for left-hand side, and then when we did the x times y, we got this on the right-hand side. So x times x naught, so if x is 0, the other is going to be 1. And so for this AND gate, it's going to always be 0 because they're never the same. So we can mark out this, and so then we're left with x, y. So those are the simple Boolean theorems that you need to know. Is
Okay.
for
Well,
these, yeah.
oh yeah. Quick question. All these will be like on the exam or like just some variation of it?
I think there will be, but I think it's more the K-maps, to be honest. I don't feel like he's going to test us much on this.
But still, it's just like a good like foundation just to like know.
Yeah. And then
Okay.
De Morgan's theorem is a little offset of these. And how I think of De Morgan's theorem for us is that if you take the naught of both, so let me draw that little naught over it. Oh, let me do that and I color that actually. If you do the naught of both, that's equal to the naught of each individual one, but with an OR gate between it. So I think of it as both are knotted together under one gate, and that equals the individual knots over the opposite gate. Because if you look at number 2, it's the exact same thing, but just sort of flipped because they're both connected.
Okay. X plus y equals. Oh, okay.
So
Yeah,
look
I can see
here
that.
is how I think of it is De Morgan's theorem is I just think both are grouped together under one operation and they're individually separated under a different operation. Both are grouped under addition here and they're individually separated by multiplication here. That's how I remember it.
It always separated by multiplication and vice versa.
Yeah.
Yeah, I see. Cause like I was always like getting mixed up with the Morgans.
Okay. And then the next one, I'm going to do an example because he gave us some extra problems and it goes well with the next one. So let's do that one. And that will be all of our K-map stuff. So let me clear and let me stop this share and let me get into the reshare just my desktop. Okay.
Okay, sure.
So for his 301, I'm going to have the problem on the left-hand side and then I'm going to have the book on the right, my work on the right-hand side. And so what I'm going to do for this one is, let me pull up which problems he said. For the practice problem number 1, he said, let's do problem 4.3. Okay, so
Okay.
looking at this, I'm going to go to 4.3.
Okay.
Let's do
Wait, I should have some.
Okay, here we go. Repeat problem 4.1 for the function f of x 1, 2, 3, 4, and it's multiplication here. So we know we're using products as sums.
Okay.
And then big M. And so this was the products as sums. And if we remember our two versions we have within is POS and SOP. I always think of it for products as sums. How I think of it is summing in the middle. So everything's addition in the middle, and then you multiply afterwards. So you go from the end and you go to the beginning. So you add all those individually in order to get your groupings. And then after you get the groupings, you multiply all of them. So how I think of it is sort of like the multiplication is outside the addition. So you go addition first when you get the specific, when you do the K-map circling, and then you multiply all the terms together after. And then the opposite you do for sum of products is you have the addition, but the product is in the center. So you do the multiplication in the middle, and then you go outside to the addition. So you sort of go from the back and you go forward. You do the product of the terms when you circle them, and then you sum all the terms together. And so I
Okay.
think of it as going from the end to the beginning because this is
End to
sum of products. And so let's do an example here. Now that we know those two conventions. And so this one says, find the minimal cost product of sums in SOP form, so sum of products, for the function x1, x2, x3, and then they gave us this format. So it looks like they want the, if we think about this, minimum cost sum of product and product of sum forms, and they want to do that for this function here. So this f of x1 to x4, and they gave us the product of sum form here. And
Okay.
so it looks like we're going to be doing that. And so I'm going to write that over here. So I'm going to have my f of x1, x2, x3, x4 is equal to, and then this pi symbol here. And that's telling me product of sums because the big pi m, that means product of sums, where the small sigma in lowercase m means sum of products.
Sum of product, and then
Oh, here, let me do it up here. This sum with the little m is sum of products because sum right here, sum.
oh, okay.
And then product, they use this pi. You can think p with p, product, and then big M.
Okay.
Because product multiplication, I think it has a greater value than addition if we go off that PEMDAS. So it has a big M, it has bigger precedence. Okay.
Okay. Okay, that makes sense.
Now let's go into the actual way of how to do it. So I'm gonna lower that. So for this multiplication, what we need to do for this product of sum form they gave us is it's 0, 1, 2, 4, 5, 7, 8, 9, 10, 12, 14, 15. Okay, I'm looking at this. What do I do? And so I know, okay, I got 4 variables here.
Okay.
And I need to make a K map, right? Because we can make a K
Yeah,
map.
so
Okay, K
yeah,
map.
makes it like that.
And then I'm gonna have, and then we have x1, x2. So let me write that.
Yeah, x1 and x2 are at the top, and then
x3,
x3 and x4 at the bottom. Yeah, like that.
And then what we're gonna do is we always start with 0, 0. So 0, let me do a different color so we can see it. 0, 0, 0, 1, and then we have 1, 1, and 1, 0. And then we have here 0, 0, 0, 1, exact same way, 1, 1, 1, 0. And so now that we know that, we know here in the big M, we're given these positions 0, 1, 2, 4, 5, 6, and all the way up to 15. And if we think about this, this is 0, 0, 0, 0, which is the 0 spot. This is 1, 1, 1, 1, if we think about it. So we're like, okay, this is the 15th spot because that's when it's 0, 0, 0, 0, and that's when it's 1, 1, 1, 1. And so now the in between 0, 0, 0, 1, that's right here.
Yeah, 1.
And then here's where it's 2. Oh, wait, no, sorry.
No,
2
wait,
here.
no.
Yeah.
Yeah.
Is 0, 0, 1, 0. And then we have 3 here. Then we have 0, 1, 0, 0, which is 4.
Okay.
And we have 0, 1, 0, 1, which is 5. Then we have 0, 1, 1, 0, which is 6. Then we have 0, 1, 1, 1, which is 7. So 6. And then we have
6, and then 7's right there.
And then we have 1, 1, 0, 0, which we're like, oh, wait, 1, 1, 0, 0, that's not 8. 8 is actually 1, 0, 0, 0, because if you do 2 to the 3, that gives you 8.
Okay, 8.
And then 9 here, because we just have a 1 added at the end. And then
okay, 9.
give us our 10, 1, 0, 1, 0. then
Okay,
11,
yeah.
1, 0, 1, 1. Then we should get
Okay.
our 12 here, which is 1, 1, 0, 0. Then our 13,
Okay,
1, 1,
12.
0, 1. And then our
Yeah.
14 here, 1, 1, 1, 1.
14. Okay. Okay.
Now
Oh,
we
okay.
know the locations, which is good. We know the locations and everything. So now we need to make our K-map full with all these. So let's make our K-map actually full for these values. And so I'm going to do my x1, x2 again here, x1, x2. And I'm gonna have my x3, x4 here. Then we're gonna have our drawing, we're gonna put in, and we split this up again into 4. So we have our 1, 2, 3, and 4. And then we have 1, 2, 3, 4. Okay, now that we've done that, and then we know we're gonna have 0, 0 here, then 0, 1, then 1, 1, and then 1, 0. And then down here, we're gonna have 0, 0, we're gonna have 0, 1, 1, 1, and then 1, 0. Okay, now that we know that, we know the spaces to fill it in. If we look here, we're like, okay, at spot 0, and at spot 0, because we're doing product of sums, remember product of sums, you circle the zeros, but in sums of products, you circle the ones. And so I'm like, oh, here I circled the 0, so this must be where the zeros are. You can always just remember it as zeros with the big M. So these are zeros, and then ones with the lowercase. Because in sums of products, you circle the ones, but in product of sums, you circle the zeros. And so this identifies where we have zeros. So if we look here at position 0, right here, and that matches up with right here. Position 1 here,
Yeah, so 0.
matches up with 1 here, so we got a 0 here. Then we have at position 2, which we identified was down here, we have a 0. And then at position 4, which was right here, we have a 0. Position 5, we have a 0, so that's here. And then position 7, we have a 0, which was right here. Position 8, we had a 0, which is right here. Position 9, we had a 0, which right here. And if we just keep going, 10, 12, 14, and 15. And it's like, yay, okay. Now we found our zeros. And so now that we found the zeros, we can replicate this exact chart and just fill it in with the ones for the sum of product. And so what I can do here is I'm gonna draw a little graph here. I'm gonna replicate this exactly, you'll see. X1, X2, and then I'm gonna have my and then just have my okay, so if we look here and if we split this up again into our 4 columns, 4 rows, what we should get is here 1, 2, 3, 4. Okay, I'm looking here and I'm like, okay, for because we found this one here, and I'm going to label this one the product of sums, since this is where we put all the zeros. And then here's going to be our SOP, where we're going to circle all the ones. And the ones are going to go in the places where the zeros weren't. So we're going to have a 1 here, 1 here, 1 here, and 1 here. And so now we're going to have to group. So for product of sums, we group the zeros together. So I'm looking here, I'm like, oh, okay, how do we group this up? What's the best way? Well, I notice we have 4 right here, because you want to start with large groups. We have 4 right here, see? And then we have 4 right, not 4, sorry. We have 2 right here. That's a good group, 2. And then I'm looking and I see we have zeros in each corner. And then I noticed there's just this one here left. I notice I can make a group of 4 here. If you see with that one here, and so if we group the zeros, we can go through each color. And when we go through each color for the red group, we're gonna get that the X1, and then X1 was 0 here. It was the same here, but since it's product of sums, you do the opposite. So that's why we don't have a bar above it. We just leave it like it is. And then let's look here. X3 stays the same, but X4 changes. So we ignore X4 and we use X3. X3 was 0 here. So instead of the bar, we do the opposite for product of sums, where we just keep it and we don't, we do the opposite. So we do the 1. So we get X3 here. And then since it's product of sums, remember, we do summation first, and then we're going to do the products after. So this is our first one for the red. And then let's go to the orange group. The orange group, the X1 value stays the same. The X2 value changes, so we ignore that. So the X1 is 1, but since it's product of sums, we do the opposite. So we do the X1 bar here. And then our X3 stays the same because of the 1. X4 changed though, so we ignore it. So we do X3, and the opposite of 1 is 0. So X3 bar. So we have here X1, and then remember it's product of sums, so we go last. So we do the summation,
combine
the product around the term. And then we're going to do the yellow group. Yellow here, it looks like the X1 value changes, the X2 value stays the same. So we're going to do X2 not, because we do the opposite. Then we're going to have X3 and X4 stay the same. They're both 1, so we do the opposite. We'll do the bar, so X3 bar, and then X4 bar. Add those together. And then we get X2 bar plus X3 bar plus X4 bar.
X3, X4, okay.
And then we're going to have the green group, which is X1 changes, so we ignore it. X2 stays the same, so we actually take that into account. So X2 stays the same, so X2, but then we notice it has 0 here, 0 here, and so we do the opposite, so we have 1, so no bar here. Then X3 changes, it goes 0, 1, so we ignore that. Then we have 0, 0, so it's the same here for X4. Do the opposite, so it will be without the bar, so X4 here. And then we have X5, which, sorry, not X5, our 5th group, which is the pink group here. We have X1, which changes from 0 to 1. We have X2, which is 0, 0, so X2 stays the same in this pink group. So we have X2, and it was 0, so we do the opposite, so we keep it 1. And then we do X3, which stays 0, 0. So we do the opposite, which would be X3 without the bar. And then we have X4, which is 0, 1. So we neglect it because it changes. So now that we got all the terms here, this is our complete product of sum here. So that's how we got our product of sum for here. So we have all these multiplied by each other. You can see X1 plus X3 is multiplied by X1 naught plus X3 naught, multiplied by then this yellow group, multiplied by green, multiplied by pink. Okay, now that we got the product of sums, we found the minimum cost product of sum, we have to find the minimum cost sum of product. And so for sum of product, we have this other one here where we circle the ones for sum of product. So this is one group I noticed. And then the other two don't share any ones around them vertically or horizontally. So they're individual groups. Okay, now let's get the resulting function from this. So for the red group, we notice that x1 changed. It went from 0 to 1. So we ignore that. 0 to 0. So that's the same. So for sum of product, we keep it the same. So x1 not. Then we notice x3 and x4 stay the same. So we just multiply those. So x3, x4. And remember that we're doing multiplication between these because its product is at the end. And then we're going to sum it with the other groups. So our next group is going to be this orange group here. And so for this orange group, we're going to have x1, x2, and then x3 and x4. They don't change. 0, 1. And they don't change. So we're going to have x1, x2, x3, and x4. And when I do that, I get this resulting function here. And then for the third group, that's going to be the exact same. We're going to add that because it's sum of products. And so adding this yellow group here, we have 0, 1, and then 1, 0. So it's going to be 0 for x, 0, and then 1, which is x2, and then 1, 0, which is x3, then multiplied by x4, and it'd be x4 not. And so x. Okay, so that's what we get for these three for a resulting function for the sum of product here. And so here's our SOP form, and then here's our product to sum form. And so let's look and compare that against what he received for his and see if we got what we were supposed to. So let's look here. We can always work backwards if not. And so for his sum of product here, he got x1 not times x2 times x3 times x4. That's our yellow group. We got x1 times x2 times x3 not times x4. Yep. x1 times, oh wait, he got x2. Yeah, I was supposed to write x2 here. Sorry, I wrote x1 by accident. So x2 times x3 times x4, and that is correct. Yes. Okay. And so let me just fix that. I just accidentally wrote 1 instead of 2. Is because the 2 didn't change here for the red group, but the 1 did change from 0 to 1. So we neglected it. Okay, now this product is sum form. Let's check. x1 not plus x4. He might have grouped them differently. x2 plus x3, x2 plus x3 plus x4, x2 plus x4, and x1 plus x3. Okay, it looks like here they just grouped all of our groups here. If you look, x2 plus x3, he did that one. That was this group here. He did x2 plus x3 plus x4, which is this group here. He did x2 plus x4, which is this group here. He did x1 plus x3. So it looks like this orange group was the only different group he did. And instead of doing the group we did here, he did for this orange group, what was it? He circled, yeah, okay, or wait, let's see, x3, x1. He did it, x1, okay, yeah. Okay, I see, because if we look at this, we're thinking, okay, this would have to be where x1 was 1, 1, and then he had to do x4, which was x1. How did he find that? Oh, I noticed I just made it. Oh, this is a 4 here, sorry. Okay, yeah, so we got exactly, oh, but he chose 1. Okay, yeah, that makes sense because for product of sums here, remember, we do the opposite. So since we had 0, 0, this should actually not have a bar right here for x4 term. Okay, so now that we've resolved that, let's go on to our So it just needed to be an X. Because the 0, 0 was the same, but remember for products of sums, we do the opposite. So instead of being a 0, we flip it, we do a bar over, so then it would become X4. Okay, let's try the next one. That's a little cleaner. So for this one, what it wants is for problem 4.33. 4.33 here, it asks, repeat this one for the following expressions, and we have them here. And so it says for 4.32, it said prove or disprove that f equals g. So we want to show here, does f equal g? And so what we're going to do is we have to create the k-maps and look if the k-maps are the same. So let's create a k-map for f, and then let's create a k-map for g. When I'm looking at these two, don't you notice these are all multiplied and then they add them? So this is SOP because they went from a product, which is multiplying all the individual terms, and they added those groups together. Then this one I noticed is product of sums, since they summed them all together and then they multiplied all the terms. And so let's do that and write the k-map here. And so let's make a k-map for f and make a k-map for g. So I'm going to have a k-map here for f, and then I'm going to have one down here for g.
All right.
So for our k-maps, let's have our x1, x2, because we notice we only have 4 variables in all these equations. x1, x2.
Okay, yeah, understand. Time x2, x3, and then x4.
And then x3, x4. Okay. And then I'm going to call this one up here. This one's going to be my f. And this one down here is going to be the k-map for the g equation. And let's draw this out. Let's make some lines. So 1, 2, 3. 1, 2, 3. Oh, that was pretty bad. Okay, and then this one. 1, 2, 3, 4. Okay, and then we'll do our 0, 0. So what I'm going to do for this one is, I noticed for the SOP, to make it nice and easy, what we can do instead is we can just label this, because we know 0, 0 is when x1 naught and x2 naught. Same thing, just writing it instead of 0, 0.
Oh, okay. Okay, so that's x1 yeah, because like I was sometimes having trouble with the understanding the k maps. I'm like, what? Because I understand like the top part on like where x1 x2 is, but I just couldn't like understand like how would I like put them down.
And so
But this
looks like this.
okay, x. Oh, okay. Now I see how.
Let me do this. Smart, because this would be 0, 0, then 0, 1, and then 0. This would be 1, 1, and then the last one would be 1, 0.
All right. X4.
Okay. Now that we got all those, what I'm gonna do here is we're gonna go turn by turn. And so let's start with this first one here. And so it's x1 times x2 naught times x3 naught. So I'm like, okay, where's x1? I notice x1 is here and here. So it can be in either of these two columns. And then x2 naught and x, where's x2 naught? That's here. So it's going to have to be in this column now, because that's where both happen. Then x3 naught. So that's going to be in these two is where x3 naught occurs. So we know it's going to be in this one here. And we're going to, because this is sum of products, we only group the ones. So this is going to be ones. So 1, 1, 1. And then let's see, x1, x2. And we notice there's only in this column, sorry. Because it was x1, x2 here. And then we had the x3 naught, x3 naught. that matches up with the 3 here. So we notice.
So wait, there only needs to be, yeah, like that.
Yeah.
Okay.
And then the next one's going to be x2, x4. So where's x2 and where's x4 here? So
Okay, so
x2
yeah, it's the second one.
here,
Yeah,
and then
one of those
x4.
two. Yeah.
So when I fill that in, that's going to be 1, 1, 1, 1. Okay, let's do next one. So this one's x1, so that's going to be these two here. Next one's going to be x2 with the bars, so it's going to then be limited if we look here. It's going to be this one,
Okay.
matches up with these. Then we have this
One,
x4 not,
yeah,
which is here.
yeah, 4 not.
So it's going to be in
So
this row, and so it's
one.
going to be here. Because
Okay,
we already have
yeah, down there.
Okay. And then our next one is going to be x2 naught, x3 naught, x4 naught. So if we look at x2 naught, that's going to be here.
That one, yeah.
And then
Okay, I see.
naught,
Yeah,
x4
one.
naught, it's going to be here. And so I got 1 here.
Yeah,
Okay.
yeah, that's what I put.
Let's look at this one, x1 naught, which is going to be
It's gonna be
yeah,
yes.
this x2, so it's going to be in this one.
Yeah, that one in
And
particular.
x3, which will be here. And so I got just fill in this one right here. That's the only one missing. And then let's now match it up with this map for G. So let's go to G and do all the ones for it. Okay, G is going to be, remember product of sums though? We flip the output so you know. So when we're looking for x2 bar, we're actually looking for x2 on the map because we flip it, remember? So when I go here and when I rewrite these, so when I do x1, x2, and x2, x2. And then x1, or yeah, this is x2. And then it's going to and then x3, x4. And then we have x3, x4 here. And then I need to add them on this side. Okay, so when we do this, how you want to go about doing it is for the first one, we know we have x2 naught, so we're actually looking for x2 if you think about it, because it's the inverse for product of sums. And so we're looking for just x2, and here we got x2 here. Okay, now we're looking for x3 naught and x4 naught. And when I do that, I'm like, okay, that's here. And remember, product of sums, we fill in zeros because it's opposite of sum of products, so there'll be 0, 0 here.
Okay, so it's in reverse, so for P.
Yeah. And so then this x1, x2, we're actually looking for, instead of x1 bar and x2 bar, we're looking for x1 and x2.
And so wait, shouldn't there be a bar over the x2 on the last one?
Oh yeah, there should, sorry. I just forgot to include that real quick. So let me just make sure there's good catch. Okay, x2 bar. X2.
Wouldn't that mean there's only a 0 in one spot instead of 2 for the first
one?
Wait,
let me just recheck that real quick. It would be here for this one because we look for x2 without the bar.
Yeah,
x3, x4, we looked for, it would be here. So yeah, right here. Okay, and now we're going to go to the next one, which is x1 bar, x2 bar. So we're looking for just these without the bar. So that would be in this column here. Oh, sorry, no. This column right here without the bar.
Okay,
and then x4 with the bar. So here's one with the bar and here's one with the bar. So it's the first and last.
Okay, so
it looks like we just need a 0.
And then, yeah, just another one like down there. Yeah.
And then here's x2, x3, x4. So if I'm looking at that, I'm like, Okay.
Okay, so you need like a bar in the first one and then the last one at the top.
Yeah, and then
And then you
here
need the
the
opposite
bar.
of that, which is in the third column right here. So
Okay,
then
here.
0 and then 0.
Yeah.
Yeah, those two spots. Okay.
Now let's do the this one here. So x1,
Okay.
x2 with the bar. So we're looking here. We're like,
Okay,
okay, this is
so
where
basically that.
this column. Yeah.
Yeah.
Then x3 without the bar. And
Okay, and
so
then it'd be down here, just only in the corner.
these two, yeah, so it'd be in this.
Okay.
And then now we're doing x1, x2, x4. And how I think of this is I'm like, okay, x1 and x2 with the bar, that'd be here. And then x4 without the bar, so that's here or here.
Okay, so
In this one. Okay, so that would mean we just need a 0 here.
yeah, just one there.
And now if we're looking at this, let's merge the two, okay? And when we merge the two, will there be any issues? If we look here and we do this specific. Okay, I'm looking here. I'm like, okay, there's a 1 here. Let's see, there's a 0, 0, 0, and then there's 0, 0, 0. We have a 1, 1, 1, 1, 1, 1, 1, 1. Did we forget a 0 here? There's nothing marked here, and I felt like
No, but we're just supposed to make sure that edges equals to each other.
yeah, and we're looking and they are equal. This came out.
So it should be a yes then.
Yeah. And so that one condition, we might have missed one, but they should be equal. Let's look what he said. If we did, we just missed one spot in here. We'd have to go back and check all them. But as right now, they look pretty equal. And yeah, so they're equal. So, and then it just said the minimum SOP function. I guess, did they ask for that? Consider, they didn't ask for a minimum SOP. If you
No, it
wanted
just
to,
says repeat and then yeah.
yeah, if you want to find a minimum SOP, all you do is you would circle, you know, the ones you want,
Yeah, then
and
yeah,
then
just
you
group
would
them.
simplify. Yeah. Okay, so now that we know how to do that, we can do his next one, which was 4.35. And 4.35, it asked for, let's see. Circuit 2 outputs is defined by the logic functions f and v equals that. Derive a minimum cost implementation.
Okay, so let me at least write down the 1 equals 3.
So we're gonna have to do the logic function for this one. I mean the K-map again.
Okay.
And so I'm gonna make my K-map and you make yours and let's check it.
So we just need to make an F and a G1.
Yep.
Okay, simply. Okay. I'm gonna write that. And it's a PO. No, wait, not a POS. It's an SOP.
Yeah, because it's products, then they sum them.
Okay. Oh, whoops. Okay. Oh. Okay, I think in the F, I was just missing like one number. Like, yeah, on the left-hand corner on the bottom.
Yeah, let me check mine.
Yeah, because like I know our G's match the same, and then yeah, I think F. Let me go back and check it.
Yeah, I worked this one out before and this is what I got. So let's see. What we would do next is you probably just made a simple mistake. We group the small terms like 2 or 1 that they share together. So if I'm looking here, they share this one here, in here. If you look on these, they share these two. Okay.
Yeah.
And looks like it just shares this one here. Shares this one here. And then I notice, so we can circle that. They share this one here and this one here. They don't share these two and these two here. They share this one here. However, even though they share this one, you could make that simpler on each by grouping it with this one here and grouping this one with this one here, then sharing them. And
Okay.
so that's the reasoning why we just then group this separately, because I asked him and he said, oh, because you can simplify it here so you don't have to add an extra, because it wouldn't actually simplify because they can group with another term right next to them. And then this one here, if we take, and then this one, let me do in brown. Okay, so then that will be all of our terms. And when I did that in multiplied, I'm just going to say it so we can go through. But what you should get in the end when I did this was, for this problem, which was 4.35, what I got was 7 total gates when I simplified it out, because I had 3 groups in the F, and then I had oh, oops, sorry. I know where I made the mistake in F. Right here. Oopsies. Those are 4 if you look right there. I forgot. These two, I'm in erasal mode. These two right here connected with these two right here. So look, these two with these. So I had 3 groups here. So 1, 2, and 3. And then here I have 1, 2, 3, 4 for G. And so I have 4 and 3. And I have 7 total logic gates. Then that would create when I wrote it all out for my minimum product of minimum sum of product. Because when I wrote it out, I got these equations here, as you can see right here in the textbook, when you implement the circuit, that's what they got here. And we can see that they overlap with two of these. So this one here overlaps with this one here overlaps with this one. So they're shared. So the only gates you need to provide is you need
Oh, okay. Well, that makes it a lot
three,
easier.
yeah, you need one 3-input OR gate. You need another 4-input OR gate here. And then we need one AND gate here to combine these terms. And then we need one AND gate here to combine these terms. Those are used here as well, so you don't need to use another gate. We need another AND gate here, so we have 3, and then we have a 4th AND gate here, and then a 5th. So if we add the pink and the green groups, we get 7 total logic gates. And that's what we'll need for this. And then what we'll do after is the last one was 4.49. Let's look at that real quick. Then we'll get on to everything else. Write VHDL code to implement the function. Okay, it has it here. And so I'm going to find the minimum product of sum for this. Remember, I told you this is sum of product because we have the sum symbol right here. That means sum of product. So this is an SOP form. And we have the little m, so that also ensures.
Okay.
And so when I go to create my K-map here, K-map time. For my K-map, I'm going to have my line. So 1, 2, 3,
1, 4, 7.
2, 3. I'm going to have x1, x2. I'm going to have x3, x4. And then I'm just going to call this f from the title of my K-map. Because that's the function, and I'm going to draw it all out. So I'm going to have 0, 0 here, 0, 1. Oh, let me just make it simpler and do 0, 1, 1, 1, 0. And then here we have 0, 0, 0, 1, 1, 1, and then 1, 0. Oops. I did not want to paste that. Okay, let me just do all that then. 0, 0, 0. Okay, and we know in spots 1, so when we wrote that out before, that was here. 4, which was 0, 1, 2, 3, 4. We have a 4 here. Then 5, 6, 7, and then 8, 9, 10, 11, 12, 13, 14, 15. Okay, so we know where our 1s are, and don't cares are at 0, 5, and 9. So 0, 0, 1, 2, 3, 4, 5. And so we have a don't care. Oh, sorry, don't care here. Don't care here. And then at 9. So this was 5. So 6, 7, 8, 9. So we have a don't care here. So we have don't care at those positions, and we need to implement the code. And so we need to simplify this. Okay, I'm going to look. I'm like, okay, this group can be simplified right here. Then I'm like, okay, these two here, how are we going to simplify? Looks like the only way we can simplify is group these two terms together and then group these two together. Okay, let's simplify this. And so when I go to write the equation for my function f is equal to, and I'm going to look at this purple group first. It looks like x1, x2. It's sum of products, so keep them the same. So x1, x2, and then x3 stays the same, so we can keep that, but x4 changes, so we're not going to include it. Then for this orange group here, since it's sum of product, it's going to be x1 changes, we see goes 0, 1, so we ignore it. x2 stays the same, so let's do x2. Then x3, x4. And then for blue group, we're going to have x1 stays the same, x2 changes. So I'm going to write x1 here. And then we notice that X3 stays the same, X4 changes, so just have X3. Okay, let's then make the circuit for this. So we're gonna have an X1 in our circuit. We're gonna have an X2 in our circuit. We're gonna have an X3, and we're gonna have an X4 in our circuit. And what I'm gonna do is I'm just gonna draw a line going down each of these. So I'm gonna have an X1, gonna have an X2, I'm gonna have an X3, and I'm gonna have an X4. And we need to make an AND gate connecting X1, X2, and X3. So I'm gonna have one going here through X1, one going here for X2, and then one going through here, X3. Then I'm gonna AND those together. So that's gonna be through an AND gate here. Then I'm gonna have one for X2, X3, X4. So what you need to do here is X2, X3, and X4. And then I'm gonna AND those. So I'm gonna draw a little AND gate here. Then we're gonna have X1, X3. So that's going to be X1, X3, and that's an AND gate. So I'm gonna have one right here. And then what I need to do after is it's the sum of all those added together. So we're gonna have to OR all them together in order to create that OR relationship. And then that should give me my F output. So we should get our F here. Okay, and there we go. So if we look at his diagram, let's see what his, oh, okay, that's the logic diagram. Okay, now that we have the equation, we need to create the VHDL code. And so I'm gonna do the code on the left-hand side. So let me open my notepad.
Okay.
And when, I'll just text edit. Okay, let's start off. And so what we need to do for text edit, we start with a library, IEEE. No, hopefully it doesn't correct all the time. IEEE. And then we're gonna use for our library, it's gonna be IEEE dot standard dot logic, and then 1164 dot all. And with and then after that, we're gonna have our, since we have a truth table, not truth table, sorry, we have a schematic diagram, we can easily describe that. And so I'm just gonna use behavioral coding for mine. We'll see though. It might actually be structural. Let me see, because we have let me just get into it. So entity, and the entity I'm just gonna call this is just like, because we're just creating it for problem 4.49. I'm just going to call it entity for logic function 499. And then I'm going to be is, and within this entity, we're going to have, you can see X1, X2, X3, X4. So we have 4 inputs. So I'm going to say for my port, I'm going to have X1, X2, X3, X4. Those are going to be inputs, and it's going to be a standard logic, ones or zeros for them. And then end logic function, because we're going to close this entity now. We declared all the ports. And now that I got in that, oh, we also need an output, because F for function is going to be our output. So let's write that. I forgot. So F is going to be an output, and that's standard logic. Okay. So now that we have all of our inputs, which are these 4 variables, X1, X2, X3, X4, you can tell, and they're going to produce the output F. And then now we need to describe the how it works internally. So you can tell here, remember, this was our equation we got in the end. So we need to write that specifically in here. And since we have an equation, he made a keynote for behavioral versus structural coding. And I have it on a post-it note here. Use behavioral when you have equations or a truth table. And so since we have an equation here, we'll use behavioral coding. And so for mine, I'm going to write architecture, behavior, of, and then the behavior of this entity, so is, and I'm gonna assign to f, so that's why I have this assign here. And I'm gonna say x1 times x2 times x3 plus, and then we're going to have, I'm gonna put this all in parentheses just so it does the correct operation, x2 times x3 times x4 plus x1 times x3. Okay, and now I'm gonna end the behavior. Okay, and so now that I know that from this diagram and that we circled all that, oh, let's see, x2, wait, I just noticed something. Wait, I just noticed, I forgot the bars on this and I wasn't told. Okay, x1 bar here, I just forgot. X3 would have a bar here as well. And so then x1 here, this one's correct. Let's see, x1, x2, x1, x2, and x3. Yeah, that's correct. And this x2, x3, x4 here, x2 is one, yeah, x3. Okay, yeah, that is correct. So I just needed this x1 and x3. So for this one, I just needed to add a not here and then not here. Okay, we're good. And so all I needed to do in this code, let me just make sure I write that here, is not x1 times not x3. And remember when we are in the actual VHDL coding, these are not interpreted as logic operators. They're interpreted as multiplication. So to do logic, you have to write and here. And then it's also for the addition, you have to write or, do and then you have to do and then you have to write or, then you have to write and here. Okay, and now that we got all those, what we can do is we can compare it against what they received. So they got the logic function x2 times x3. Yeah, they just took out the x2, x3 and did x1 plus x4. That's totally fine. We got the exact same result. Library IEEE, use standard logic. Yep. Entity logic function, x1, x2. Yep. And then they ended it and they had the behavior. Okay, it looks like we did that correct. And we wrote it all. So we ran through the code basically right here. If we do an overview, these are the two libraries we need. This one's for the logic because we're using and or gates and not gates. Here we have our entity and we have the ports. We have the input ports. We have the output port here. And then down here is the behavior. And so for the behavioral, we use behavior because we had an equation for F. We wrote it over here, underlined it in green, and we just described all the logic there and we ended the behavior. So now that we've done that, we've done all the practice problems. Okay. And now let's get to the rest of what he did. So now we're going to move on to the actual VHDL part of it. So let's go to what he has in his actual table of contents and go to the slides. Okay, so VHDL, let's just get a little background on this. It's just a very high integrated circuit hardware description language. Basically, we're just going to be doing simulations in it of what we receive. And so here's how the code looks. We're going to have a library. This library here, you have to include with every single file you do, the library IEEE. And then these down here, this one's used for standard logic. So your and, not, or gates, where these two here are used for like multiplication, division, addition, subtraction. And so you know when to use each. And now that we know that, we're going to look at the entity right here. So entity of our circuit 1, how we can express the entity part is we can write right here. If we have circuit 1, it has A as an input, B as an input, C as an input. Then we have F as an output here. So it's on the other side. So we can express A, B, and C as coming in to the entity, and we can represent F as a variable coming out. And so that's how we describe it right here. For entity, we describe all the ports coming in and ports coming out. The architecture behavior is what happens inside the entity. So the behavior, behavioral coding we use when we have either a truth table or equation given. And so what we have, the behavior circuit 1 is, and then we have an internal signal. So we write signal, and then we call the internal signal by specific name. We have F1, F2. Then we use the colon, and we declare it as standard logic. So that means it's either a 0 or a 1 as what it can represent. And so for standard logic, what we have here is F1 and F2. So I'm just going to write F1 and F2 here because they're inside, they're an internal signal within this. So F1 and F2. And what it's going to say is down here, we assign to F1, A and B. And so if we look at here, F1 is going to be the combination of A here and B ANDed together. F2 is going to be C and not B. So we're going to have B knotted. And so here's the knot of B. And then here's an AND gate. And we also have C connected. So we have a knot for B, and then we have C also connected with the AND for B. So let me draw that better for you guys so you can see what's happening. And so let me space this out a little more. So let me put, man, can't erase that. Okay, what I'm gonna do here is we have not B, so that looks something like this. And then we have C here, and this would be F2. And then the final statement says F is assigned to F1 or 2. So we're going to have the F1 here and the F2 here and the OR gate. So here's our OR gate here. So it's going to be F1 or F2, and it gets assigned to F. And we end the behavior. So that's how it works, is we have our entity, and then the behavior describes the internal circuitry. And now that we've done that, let's get onto the next slide. So closer look at our code. We have a library here. We have our packages, and we have the port statements within the entity. So you know, VHDL is case insensitive. It does not matter if you have upper or lower case. And now we're going to go down at the code. So as I told you guys here, the architecture behavior, you need to use architecture to describe the behavior of the circuit. To start out, it's just like the key word here. And then you either say behavioral or structural. Behavioral, used for equations or truth tables. Structural, used for components, port map, or schematic. And so then we have our internal signal. So we say signal, another keyword. And we'll call that signal F1 colon, and it's going to be standard logic. Signal F2, and that's what we'll call it, colon, and then standard logic. So 0, 1s, and begin, and we're going to give it the internal circuitry here. So that's where we have the A and B connected to F1, the C and not B connected F2, and then F was connected to F1 or F2. Okay, now that we've done that, we're going to look at concurrency. So concurrency means that it can run the code in any form. So it can run it downwards, it can run it upwards. So from bottom up, up, down. When the compiler does it, it can run it just like 1, 3, and then it can go back here. So it doesn't matter the order of the statement. So you can write your code in any order you want, but I suggest you write it in an order that makes sense. And so, you know, the assignments can be any certain method you want. Okay, now what we're gonna do is let's look at how this one is actually looks. So I'm gonna draw this one out. So we have all of our libraries here. So what this library tells me is what we can do is we use the main library, and within this big bookshelf is what I like to call it. We're going to take out the book that can do logic gates here. So this one's used for logic gates, and these two here are going to be used for multiplication, division, addition, subtraction, division, and multiplication. So any order of operations, that's what this unsigned one's used for. And now let's draw it out. Let's see what this looks like. And so drawing the circuit out, I'm going to call it example 1 because that's the name of the entity. And we're going to have ports A and B as inputs, and we're going to have C and S as outputs. And I'm looking at this and I'm like, okay, now let's look at the behavior. So it assigned here to C, it gave it A and B, and then it assigned to S, A, and then XORed with B. So let's do that out. So with C, it got assigned A and B. So A and B is the C. And S was A XOR with B. So A here, and then XORed with B. So we have this XOR, and it's connected to S. So that's the internal circuitry we have here. And that's how you would draw it out. And let's go to the next exercise. So VHDL has an entity where you define the ports in the architecture, which defines the operation, so the internal circuit. And so looking again here, how would we do this? So we say entity, then we give the name of our entity, then we say is, and then we say port, and then we list all the ports going in and out. And so here we have our model 1, because that's the name of it. And within model 1, we're going to have A as an input, we're going to have B as an input, we're going to have C and D also as inputs. So let me write those back here. So we have A and B, C, D. So A, B, C, D. And then we have E as an output. And so now that we've done that, that basically describes our inputs and our output. And now let's look at the next one, which down here. What we want to say is when we declare something as an input, like A here, B, C, and D, that's an input port. When we declare it as an output port, it can only be written to. So E is our output. You can't use it as an input. In buffer, that can be an input or output as well as in out. So if you have to take the output and reread it in the code, you'll declare it as either a buffer or in out. So if you have to reference it more than once to use it as an input for other ones. Okay, now bit means you can only have the values 0 or 1 here. And so that's a bit, 0 or 1. Bit vector, you can hold vector, so like certain amount, so you can have multiple bits in here, so you could have like 0, 0, 0, 1, 0, something like that, vector bit values. Then Boolean, it's true or false, that's what it means. Integer is a range of integer values. Standard logic, it's 9 values to indicate the value and strength of the signal. Standard logic vector is a vector standard logic values. And so, you know, when you use standard logic and standard logic vector, you need to have that IEEE package at the very top. And so that's when you say like library IEEE, that's where it's coming from, because when you use standard logic and standard logic vector. And so now that we know that binary values are 0 and 1, standard logic 0, 1, Z, don't care. We usually just use standard logics as 0, 1s. You don't have to care about the rest here. Maybe you'll see unknown here. That's really it. But the rest we don't care about. Okay, now that we know that, we're going to get down here and vector types. A bit vector is an array of bit objects. And so that's like 0, 1, 1, 1, 0. It's whatever you want for your bit objects. Standard logic vector is an array of standard logic objects. So here we declare it. So within our model 1, here, let me show you how this would look, because it's important to understand how this would look on a schematic. So if we have here our model 1, let's call it our entity. For input, we have A1, A2, A3, A4 as our inputs. And then now we have our outputs, which is B7 and B6 because it's going down to B0. So then B5, B3, B2, B1, B0. And then we have C out 1 to 0. So then we also have Z1, C2, C3, and C4. Okay, so now we have all of our outputs here, so you can see how those work. So on each side. So when we put in, when we assign 1010 as the input, that's going to cause, when we signed up to C, that results in C1 being 1, C2 being 0, C3 being 1, C4 being 0, because C goes from C1 to C4. And then B, though, goes from B7 down to B0. So if you assign it a value, then it's going to go from B7 all the way down B0. So what's this saying here is this is C4, and then it goes all the way down to C0, where this right here is going from B7 all the way down to B0. B7. This is going from, oops, I made a mistake right here. C is going from 1 to 4, so it should be C1 all the way down to C4. Okay, there we go. And so that's what it should look like. Okay, now that we know the vector types and we know how it is, we went over the architecture. Basically, how it's laid out is you declare your internal signals here. So you use the keyword signal, and then you give the name of that signal, and then you do a colon, then you say standard logic, and then you have the colon for the end of statement. You do that again here, signal, keyword, then you say the name of the signal, then colon, then you give standard logic. You begin and you do concurrent assignment statements. And then, so these can be read in any order, doesn't matter. And then you end the behavior. So you just use the same name. And then you end statements always with semicolons, just remember that. And now that we've done that, that's basically all that goes into VHDL. So, you know, VHDL has a precedence, and within its precedence, just be careful because it starts with not and division. So if you want to carry a specific operation, just use parentheses because it can't tell the difference between and or. So say if you had X and then plus Y multiplied by Z, it would first do X plus Y, and then it would do Y plus times Z. So if you wanted to do Y times Z first, you need to put parentheses around it because it doesn't know about the order, so you know. And so that's a good note to take on. Just be careful in VHDL about that. Use parentheses.
Okay.
Just like this, what they did here, X1 and X2, or X3 and X4, because they did it around.
Okay.
Because it would just go left to right and it wouldn't care about the order of those. So just be careful. And now that we talked about that, let's go to slide number 2. Okay, so this is when we use when, else, or with select. And so
Okay.
with select is important because what you do is within your architecture, you just say with, and then you give the specific variable you're going to use for your select. And so this one we're using S as our variable for select. And then you say with, and then the variable, and then select. And then you say what you want to assign it to. So F you want to assign it to. It's going to be F will be assigned A when S is 0, 0. So if we have a multiplexer here, it's basically just saying, and let's say we have S1 and we have S0 here.
Okay.
And when it's 0, 0, and this is A, that's going to produce the output F. When it's 0, 1 for the multiplexer, and we have B here, that's going to be put to the output. When it's 1, 0, it's going to be C. And the only other condition would be 1, 1, and that would be assigned D. F would get assigned D. And so that's how we use with select. It's usually used with multiplexers. And so that's specifically how we implement it. And then let me get
Okay.
into when,
Yeah, because this is more like the her and lab 3.
yeah, so you'll use always when others for all the other conditions. And so
Okay.
just remember with select, you go with the variable you're interested in. So like S, it usually is select, and then you say the output. So F, assign it, and then A
Okay.
when
So
0, B when 0, 1, C when 1, 0, and D when others. And be careful because when you're giving the list of these, they don't end in semicolons, they end with commas. And then at the
okay.
very
Oh
end of
yeah.
your statement, because that's the end of assigning F, you use a semicolon. So it's at the
Okay.
end of
So
assigning.
that's why.
Yeah. And so just be careful of that. And then we're going to go to when else. So
Hmm.
when else, it's basically a little different because you just have the output variable you want to assign it to. So assign A to F when S equals this, else B to F when S equals this, else when this, else do then just assign D. So it's a little different because it's still the same thing. You can use either or. It's just S1 here, S0 when you have your 0, 0, 0, 1, and 1, 0, 1, 1. You're going to assign these to F, and it's going to be A 1, 0, 0, B 1, 0, 1, C 1, 1, 0, and D 1, 1, 1. You can see it's the exact same implementation. Notice they don't have commas here, which is nice because they're not listing it off, but they do have a semicolon at the end as well. So just be careful on that.
Okay.
And now that we talked about that, so we did with S select, and then you say the output, assign it to A when like 0, 0, and then and then you do the commas for the list of them. And then when you have the when else, you just do the output, and then you assign it, and then you say when, and then you do that variable for the selecting
Okay.
equals this else. So let's make a little chart here when to use with select versus when else. And so you're going to have for with select, let me say here, it's going to start out the general form with, and then the variable you use for selecting, and then select, and then you're going to say F is going to get assigned A when when 0, 0, because it knows which variable you're selecting already. And then it's going to be B when 0, 1. Since you're listing, 0, 1, when you're listing, you do commas in a list. C when 1, 0. And then finally D when others. And then the end of your assignment, so you use a semicolon. When else, it's nice because you can just say when. You don't have to mark it out. You just say your output variable. So F is going to get assigned A when S equals 0, 0. And then else, and then you're going to say B when S equals 0, 1. Else, C when S equals 1, 0, else, and then finally D. And then you use the semicolon at the end of your statement. So it's similar formatting. It's just dependent upon what you want to do. So you can either assign it one way or the other. So that's how you do with select and when else. And now we're going to look at a multiplexer here. And so for a multiplexer, you can see we have the entity. We're going to be using standard logic. And so that's why we have this library right here. And so we're going to call our entity mux 4 to 1. And it looks like right here, we're going to have, let's look at W0, W1, W2, W3 as inputs. And then we're going to have S1 and then S0 because it's 1 down to 0. And then we're going to have F as an output here. So that's what it's going to look like here. So that's nice to at least have a visual. And now we're going to go through the behavior. So with select, so with the variable we want, select, and then our output is going to get assigned to W0 when it's 0, 0 here. And then when it's 0, 1, it's W1. W2 is when it's 1, 0, and W3 is when it's others, which the other case would only be 1, 1. And so that's how we do it. Then we'd end the behavior. Now that we talked about that, let's get into the actual implementation here. So now we've done all those slides. So let's get to the third slide. This one's going to go a little more coding so we can see it. So this is going to be a decoder and an encoder. So let's go over those two because, okay, one important thing which I found really weird, but I feel like it's a good nuisance to remember, a nuance, sorry, is enable is used in decoders. And then when I looked at encoders, when looking at his code, I noticed there's no enable. Look, like there's no enable pin. So encoders don't have enable pins, but decoders do have enable pins. And I was like, oh, whoa, that's a weird thing, but it's noted in his. Okay, so let's go to decoders and then we'll go into encoders. So a decoder, how I think of it, if you're decoding something, you're gonna convert it from binary to decimal. And so it's gonna turn into a longer number in the end. And so we're gonna have, for inputs here, I'm gonna draw it out so it makes more sense. So for a decoder, just so you can observe how it goes from less to more, decoder 2 to 4, we're gonna have W, so we're only gonna have 2 pins because if it's 2 inputs, W1, and then we're gonna have W0, then we have an enable for a decoder, and then we have an output, so we're gonna create 4 outputs, so it's gonna be Y0, Y1, Y2, Y3. Okay, so we got 4 outputs, we know that. Okay, now that we have that for a decoder, we're gonna have the behavior the decoder is in the signal. Right here, we're gonna declare an internal signal, which is this in ENW, and that's gonna be 2 down to 0. So in here, we're gonna have ENW. So let me just, I'm gonna draw this just bigger so we can see the entity, because I noticed that's not large enough. So just pretend the decoder is this size. And then we have W1, W0, and we have enable. And then on this side, we had all the outputs, Y0, Y1, Y2, and Y3. Okay, now that we know all that, we are given, so we know the ENW is going to be concatenated. This and symbol here, so you know, declare your signals right before you begin the behavior. So then use begin. So good nuance to pick up on. You declare your internal signals before you do the begin the architecture. And so ENW here is going to be the enable pin and the 2 input pins. So ENW, how we look at it is it's going to be enable, and then it's going to be W in 1, and then W0 because W goes downwards. And so that's going to be our array now. So ENW for this vector for 3 variables is going to hold these values. And so we know that's going to be the select now. So we know what's going to happen. So with this variable select, and then have your output and say the output is going to be equal to, and then assigned 100, 1100, and 0100, 1101. And so what it's going to look like is basically we're going to have our decoder taking place, and our decoder is going to have these select pins. So if you remember sort of from the multiplexer, it's going to have our specific values. So it's going to have the 1, the 2, and then the 3. And then it's going to be looking at those. And if the enable pin is on, then it's going to look at the next 2, which is W1 and W0. And it's going to see, and when we look at this, describing it in terms, So we know this is 0. And so our Y output is Y0 to Y3. So let me draw a truth table just so you can see this better. Okay, so within our truth table here, we're going to have the ENW, which we know is just enable W1 and W0. And that is all within ENW and W. And then we have Y0, Y1, Y2, Y3. And so that's how it's labeled here. And we just got to go by it. And we said here, assign, because when we have enable here, none of the other conditions matter. We're just going to have it being 0, 0, 0, 0, because no decimal is going to be for that. And so then when enables 1, then we actually care about the values, because then that means, oh, we're going to start decoding now. And so nothing's going to happen when enables 0. So that's why all of our outputs are 0. Okay, when enables 1, then we're going to run through all the scenarios. And the only scenarios we have here would be these other 4 here. And so when it's 0, 0 in binary, in decimal, that means 0. So our decimals on this side, because we go from binary on this left-hand side, binary, and then here's our decimal equivalent. So Y0, so at the 0th place, it's going to be 1, and the rest will be 0. And then the next one, it's 1. We can tell in binary 0, 1. So at the 1's place, Y1, it's going to be 1. Other 0, because decimal equivalent of 1 in binary, 0, 1, which is 1 in decimal. 1, 0 in binary is 2 in decimal. So at the 2 location, that's where it will be 1. And then 1, 1 is 3 in decimal. And so that's why here we'll have a 1 and the rest will be 0, 0, 0. And so how we assign this is because we had a truth table, we used a behavioral statement. And that's how we did it using the with select. Okay, remember you need an enable pin for decoder. Now we're going to look at an encoder. So this is going to be from decimal to binary, and we're going to have W and Y. And so, you know, within our entity, it's basically going to look like this here. So for our port, what I like to do is I always like to draw out sort of how the entity looks, encoder 422. And it's going to have a W3, W2, W1, and those are going to be our 4, and then we're going to have Y1, Y0. And basically what's going to happen is within it, so for the behavior, so for an encoder, we have to think about what the truth table is going to look like. So we have this W3 here, we have this W2, we have this W1, and we have a W0. And then we have this Y1, Y0. And now knowing all those values, what we have to do here is we have to actually find out how to convert these. So in decimal, let's say we have 3 as our value here. If we have 3 as our value, in binary, that's 1, 1. If we have 2 as our decimal value, then in binary, that is 1, 0. If we have 1 as our decimal value, that's going to be 0, 1. And if we have 0 in decimal, that's going to be 0, 0 in binary. And basically, that's our condition just for any of the others. So now when we write our code, the with the variable, so the variable that's going to be influencing the output is this W. So with W select in Y, your output is going to get assigned for the value of Y, 1, 1. Let's just look here, when 1, 0, 0. So that runs through this entire row here. Is 1, 0 when it's this row here. And then 0, 1 when this here. And then, oh yeah, sorry, because this is in the zeros place. For 0 in binary, it's this. And then if it's any other, let's just say like if it's like randomly like 1, 1, 1, like that's not a decimal because it's not like a 3, it's not a 2, it's not a 1, it's not, it can't be 4 numbers at once. So for any others, we just say here, don't care, or unknown. I believe that's what this means, the X, unknown when others. And so that's just the way they wrote it for the encoder. And then our component, so we know a component, it's basically, if you want to use it in another file, you can declare it as a component. So if you want to reference another file, you say component, and then you declare it. So let's look at that a little. So if we want to declare, let's say circuit 1 is stored in another file. So this circuit is actually stored in like a file over here in my computer. And I'm in right now in this file, which is right here. So if I want to reference circuit 1 over here, I create a component of it. And so for my component of circuit 1, I say component, my keyword, circuit 1, and I copy all the ports that were declared in here. So I do the exact same ports, copy exact word for word, letter by letter, character by character. You copy the ports, then you say end component. And that's how you can use a part that was declared in another file. And so what you need to know is when you instantiate the component, you have to give it a name. So you can say like example 1, some people like saying UUT, there's a specific terminology behind that. I forgot what he said. Use a colon, then give the name of that specific component that you just said. So in the other slide, we said circuit 1. And so you guys know, and then say port map, because now you need to map all these. So you're going to map them. So start your parentheses. This is the component. So the component and then the actual port where it's going to go to. And so for the component port, so you can see up here, we had all of our component ports. That's where that's taken from. And so all these component ports, you're going to have to assign them to the actual port you're using in that file. And so right here, what we have is we have entity circuit 2. And so circuit 2, it's going to have all these. So let me draw it out so it makes sort of sense, because this will help a lot when you actually see it. So we have circuit 2. Let me just label this circuit 2. And here I have NT, BT, CT as my inputs, and then I have YT as my output. And I'm looking at this, and behavior circuit 2 is, and so we reference this component here. And so when we reference this component, and we're referencing it from their files, so we copied all this from another file here, and then we declared our internal signals. So we have a wire sig, which we set, some people like to set initial conditions for this. And so that's what they did here. They just set an initial condition. And then we began the behavior. And here is where we instantiate the component. So we make one of it, and then we do something with our internal signal. So we're going to make one instantiation of the component. So I'm going to show you that will go inside this. So we're going to have an internal little guy here. And within our internal, it's going to be example 1, because we made instantiation of component 1. So, instantiation, that's where this is coming from. And so it's going to map in here. So we remember for circuit 1 up here, it has A as an input, it has B as an input, it has C as an input, and then as its output, it has Y. And so we're going to go from, when we do port map, we do it from the component part to the actual circuit part. And so we're assigning A to AT. So we know these two are connected. We know B to BT. So that's going to be here. C to wire sig. And so wire sig, if we look down here, it's CT and DT ANDed together. And so this is going to be wire sig right here coming from that AND gate going into C, and then Y to YT. So Y to YT is just going to be here. And now that we got all those declared, so we have all the ports matched up, we can end the behavioral statement. And that concludes our circuit. Okay. And now we're going to go to slide number 4. And so for slide number 4 in VHDL, what's going to happen is we're going to go through a few examples here.
Okay.
And so for these examples, we're going to go over adders. Okay.
You mind if I just take a quick drink? I'll be right back.
Yeah, let's take a minute break.
Yeah.
Okay, ready?
Oh, yeah, I am. Yeah, I do.
All right. Now let's get into adders. And so let me draw this out real quick because we have our entity adders here. So let's see how this works. I'll move this over a little because I know it's going to take up some room. And let me draw it out. Okay. We have adder here. And we have C in, and then we have X. Let me draw this just, let's see if this will be C in going to make this most logical. Let me put C in here on the right-hand side, just because I know how this works. X3, Y3 here. X 2, Y2. X1, Y1. And then X0, Y0. Okay, and then let's look at how this is going to function. And so within our adder, these were the first two, C and C, and then we need a C out here. Then we need an S as an output, so we need S3. Then we need S2, S1, and then we finally need S0. Okay, now we got all of our outputs, all of our inputs for this entity statement. Now the structure, we know with structure, you're able to make a schematic from it. So that's why I drew this. And so within our schematic, we have the signal C, which is going to be 1, 2, 3. Then we're going to have a component full add. So full add here is going to have these ports. So it looks like down here, we make 4 instantiations of the component. And so you can see we declared our internal signal, we declared our component, and then we ended the component, and now we're going to begin the actual structure and end it. And so we need to do signals and components before the structure. And so I have full add, I have 4 of those. You can see 1, 2, 3, 4 here. We have 4 instantiations, so let me create 4 blocks. So 1, 2, 3, oh, oops. Let me make those better size. So let me make this one over here. 2, 3, and 4. And there we go. And so now that we have that, we know within each of those components, we have a C input, and then we have an X input and a Y input, and then we have an S output and a C output. So what we have here is we have an X, and we have a Y, and then we're going to have a C out, and then we're going to have a C in. So I'm going to just put that in here, and then we're going to have the S, and I'm going to put that at the bottom of the component. And so that's how I'm going to write up this one. So each one, let's do that. So then this one also, because we have 4 instantiations of the component, we're going to have 4 of these within our circuit. So we have the second, and now here's our third. So X, Y, C out, C in, and then we're going to have S here. Then we're going to have our fourth, which is X, Y, C out, and then we're going to have C in, and we're going to have the S down here. Okay, now that we have the 4 components, we're going to actually now connect them up. And so we notice here, what they did is they did an abbreviation. So instead of saying from the component part to the actual entity part, they actually just said the entity part, and that was it. So from the component part, you have to do it in the specific order you gave. So C in to C in is what it's saying here. So for this first one here, so I'm going to label all these. They had stage 0 for this one. Let me try making it a different color and decreasing the font so we can have it. So this is stage 0 right here. This one is stage 1. This one is stage 2. And this one is stage 3. And you're probably wondering how I knew the specific order of that. The reason I knew the order is because if I look up here, I was like, okay, the next one here, X0 is going to go to X. So the closest one here, I just was like, oh, this is X0 to this one, Y0 to this one. And then if we keep going along those instantiations, S0 will go to S. And the reason for all these is because they shortened it. So they did it from the component part to the entity. So instead of saying the component port, they're just saying you have to read this as C in here to CN, and then X from the component to the entity of big X0. And so they're just matching them all up. And then C in to C in. And then they're going to say for S0, match it with this one. And then the C output is going to be to that internal signal we had up here, which we had 1 to 3 of. In that C output, we can tell for the input, it's going to be for that C1, it's going to be connected to the input of the other. So we're going to have our C1 right here. So C1, and then we're going to have x1 connected to the x here because they simplified it. Remember, it goes from component to entity. And so then component matching it up, the third one declared in the component was y. So matches up with the third one in the component. So we go y to y. Then we have s to s1, and then we have c out to c in. That's going to be c2. So we know, and then it's going to do that. And we're going to keep doing that for all the other ones. It's going to match up c out to in, and then the y's, the x's, and the y's, the x's, and then it's going to be C3 here. And so that's basically how we do all the coding. And what they did here is they just went from the component to the entity. They matched it all up. You can see right here, they wrote this line different to actually show you how it should look. So up here, it should say actually X is mapped to C in, and it could say Y is mapped to, this one right here is going to be from the C in is mapped to C in on the entity. This one's going to be X is going to be matched to X0. So from the component to the actual big X 0, and then this one here is going to be, that's how they could write it, and this one would be Y is going to get mapped to actually Y0, and then S is actually mapped to S0. So they could have wrote it that way, but they shorthanded it and just said the entity parts. And so that's what it looked like for the adder, because if you put one in here for your input, and then it's gonna move it up and it's going to calculate them together to get the specific bits. Now we're going to go over and do our next one. And our next one was on the 16:1 multiplexer. So how we made this is we had several 4:1 multiplexers. So instead of one large multiplexer, 16:1, we used a 4:1, and we can tell if we set these up is if we had specifically here W0, and then if we had W1, and then we had W2, W3, and then here we had W4, W5, W6, W7, and then down here we had W8, W9, W10, W11, and down here we had W12, W13, W14, and W15. We noticed here what was happening was then we had those all as our inputs, then we had the specific select, so that would select the specific value W, and then here we have other selects, so those would then specify even further, because we have 4 outputs from this. We only want one W get selected in for 16:1, so just select one from these 16. So we had to have another 4:1 multiplexer here in order to choose that specific value W, because this would carry one output of the 4. This would carry one of the 4, one of the 4, and one of the 4. So we finally needed one final multiplexer to give only one of those specific 4 from the other ones. And so now that we covered that, we could show this in code actually. So our inputs here, we had 16 values for W. So that's why here we had 0 to 15. For select, we had our S0 here. So S0, S1, S2, S3. So we had a vector 3 down to 0. And then we had our F as our output. So the final output of all this. And so we could represent this with schematic. So that's why we could say structure. And so structure of the entity. So that's where the entity is. Declare your internal signal, declare your component, and then finally begin the actual port mapping. And so for this, what we did specifically is we put all these ports together, declared their specific ones. So if we see for the 4:1, we can use one of these and multiply it by 5 because we have the exact same multiplexer here. We just need to create one multiplexer and then use it throughout. So we're taking this from another file since it's a component. So somewhere else in our computer, we already wrote the code for how a multiplexer works. And we're just taking all the ports here from that 4-to-1 multiplexer. And we're going to reference those. So we're going to take this part that we wrote in another code, and we're going to make 5 instantiations of those 4-to-1 multiplexers. We have 1, 2, 3, 4, and 5 multiplexers if you look here. So that's why we have 5 instantiations here. And we're going to, when you do the instantiation, you give each one a name. So mux1, mux2, mux3, mux4, mux5, and you say the entity it's the component, sorry, it came from. So mux 4-to-1, 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 and you just do the port mapping. So we're going to match, if we look here, how they match it up is they do it from component to entity, and they use shorthand here. So they only gave the entity. So what you need to do is you notice that the entity, the component part to the actual entity part, it's going to give W0, W0, W1 to W1, W2 to W2. W3 is going to get assigned to W3. And then the S1 down to 0 is going to get assigned to this S1 down 0. Then this F is going to get assigned to M0. And so what you can see here is they're going to call this M0. This is going to be M1. This is going to be M2. This is going to be M3. And then that's where these ones will come in. They will, from the actual output, when you assign it from the component to the actual entity. And then the last one will actually be your F, so the actual output of the entity. And so that's how you do the 16-to-1 multiplexer. You started with your entity file. You declared all the ports that you had on this. So within your entity, so outside, any of the ports outside of this instantiation here. So that's where we did our inputs and output ports. So we had W and then our S's and then our output for F. And then we did the structure coding because we have a schematic. We had an internal signal here, which was this M0, M1, M2, M3, because it went from one component to another. So that's why we have an internal signal. And then we had our component, which was this multiplexer. So if we just created 5 instantiations of this multiplexer, because we had 5 multiplexers, 4-to-1, that's what we did here. And this was already all written in another file, so we could just use that. And then we were able to begin the instantiation and say which component we used, which was the mux 4-to-1 here. And then we port mapped from the component to the entity, and they short mapped it. Instead of saying W0 to W0, W1 to W1, W2 to W2, W3, W3, S1 down to 0 to S1 down to 0, they short mapped, and they just said specifically what they wanted. So, you know, and then down here, if you want to use a for generate, what you need to do when you do instantiation is at your begin line, you're going to have to use G1, and then you say for I. So you start I out at 0 and go to 3. So you're going to create 4 instantiations here. Generate, that's your keyword here, generate. And then you're going to do the specific instantiation, which component you take that from, and then port map all of them. Then you end generate, and then you give the actual final, if you want to add another instantiation, you can right here. And then you have to end the structure. So basically for the for generate, what you have to do is you have to do, you give a name for this for generate statement. So you just say G1 for generation 1. You do the for loop. It's a variable I goes from 0 to 3. So we're going to have I0, I1, I2, I3. So we're going to have 4 instantiations. In generate, then you're like, okay, you need to start generating. And generate's a keyword because you have to end the generate statement. But for all these, you're going to call it muxes. Mux 4-to-1 is the component you're referencing. So similar to this one where you give it a name and say the component, then you port map all of them, and then you port map, then you end the generate statement. So you lock it, so you finish the generate, and then you, if you want to create any more instantiations, then you can write them below if you didn't have them in the generate statement, and then you finally end the structure. And then, so you guys know that's how you can do a for generate statement. You probably won't need to know that. It was just an extra assignment for the honors section. Okay, let's get into process. So a process is a concurrent statement. So the process can occur whenever in the code. However, the statements inside a process have to go sequentially. So that's a different manner. And so let's look at this. So in a process, the signal assignment will only take effect at the end of the process. Unless there's a wait statement, then it will assign the signal beforehand. And then it will assign it after. Because if multiple assignments are made to a signal, only the last one will take effect if there's no wait statement. So let's say like for A, I assigned it something up here, like 1. And then I had some other code, no wait statements in between. And then I gave A the value 0. And the only value it's going to save is this A is equal to 0. And when it gives the actual output. So you guys know, because process is handled sequentially, so it goes from top to bottom, all the code within a process. However, a process statement by itself can be concurrent because in your code, it can do a process at any time within it. And so it's interesting because the statements within a process are sequential, but outside a process statement, like it can occur at any time. And so let's go into it a little bit, and then let me show you how it works. So within a process, the majority of what you're going to use is wait, if, case, for loops, while loops, because those are sequential statements and they only appear inside the process. Outside the process is the with, select, and the when else. So you'll use those. So like the with select ones, those are outside the process. And that's the equivalent of like the if and then the when else. And so that's when you guys will be using those outside the process statement, but within the process, you use the wait, if, case, for loop, while loop. And so that's good to know. So let's go down. And let's look at this one. So process. These are your specific variables. So if there's a change in one of these 3 variables, it will go through the process. If there's no change in those variables, it will not execute any of this. A lot of the times what we put in these are like clock, because clock changes periodically. So whenever the clock edge happens, that's when we usually like to use a process statement. Or asynchronous signals such as like clear stuff. That's usually when we use processes the most. And so let's look at this. So we have our if statement inside the process. We start the if, else, and then end if. And so this if statement basically says, if there's a change in select x1 or x2, start the process. So we start the process. If select is equal to 0, then assign f to x1, else assign f to x2. So that would mean if select, it's probably then 1, and then assign it to f. And then end the if statement, and then we end the process. Down here, we have the actual process, and we say begin, and then f as our output, assign it to x1. If select equals 1, then assign f to output x2, and then end the if and the process. So if there's any change in these 3 variables here, x select, x1, x2, it's going to start executing this process statement, and it's going to run it down, and it's going to go sequentially and start assigning. And it's going to work as a typical if statement if you've ever dealt with those. Now let's go down and let's review the next ones. So we know how an if statement works from our beginning programming classes. And so a 2-to-1 mux. So we have two versions. He'll want us to use the version, let me see, I believe it's, look at both of them real quick. Let me see. Yeah, both can work. Okay, so let's just decipher each. So library IEEE, you always start out with these two. I always do in any code. And then entity mux 2 to 1. So we're gonna have our little multiplexer here. Oops, sorry. Multiplexer here. And for a multiplexer, we're going to have W0, W1, and S as inputs. And our output's going to be F here. And so for a multiplexer, W0, W1, and we're going to have our S. And so, oh, I should probably draw S up here because usually it's the select. That's the variable they use for select. So S here, and then our output is going to be F. And so I'm going to represent that. And so we have F as our output. And so behavior mux 2 to 1 is, and so if there's a change in W0, W1, or S, it's going to go through here. So if F is equal to 0, no, sorry, if S is equal to 0, then F is going to get assigned to W0. Else, that would mean if S is probably then going to be 1 if it's not 0. So assign F then to W1. So it's just dependent on this select symbol, and then end the process, and then end the behavior. So you're shutting the process, and then you're shutting the behavior. Over here, exact same thing. The only difference is how they coded it internally. So same exact everything. If you look here, all the entities correct, and then the process, it's just what they do here is they initially just assign F to W0, then they check if S is equal to 1, then assign it to W1 as the alternative. So they just do a cheat hand method there where they assign it initially and then they just reassign. Because you know how to process, if you assign it more than once and there's no wait statement in between, it will just then take this one and at the very end, it will just assign F to the last thing you assigned it to. And so now that we know that, we're going to go to a priority encoder. And so let's see how a priority encoder works. And so we know encoder, we need a truth table for it. And large reason why we have behavior here, which is a keyword for truth table. And so for a truth table, we're going to have our W as an input, and that's going to be 3 down to 0. So W3, and then we're going to have W2, W1, W0. Then for output, we're going to have Y1, Y0, and we're also going to have Z. And so let me space these out a little more so you guys can see them better. And what we're going to do is for the encoder, what's going to happen is it's going to go, and the encoder is going to see which one is the highest. So if we're doing numerically, the encoder tries finding the variable that is on the leftmost, and it will represent that in binary form. So if you have a number that's in W3, it will give it the value of 3 in binary. If you have, though, a 1 here, let's say it's not the one that's to the leftmost, so it doesn't care about that. And so the priority encoder, basically what happens is it doesn't care about anything that's past that point. It only cares about the digit that has the highest priority. That's the most significant bit. And so here, if we have a 0 for the first one, but we have a 1 for W2, then it's going to represent that automatically with 1, 0. And the rest are don't care, because it wants only the most significant bit. For the next one, if we have 0, 0, 1, and then we have whatever value here, we don't care about. So that's where we represent it with a D. And then it notes that that's in the ones place, so 0, 1. And then finally, oh man, this delay. And then for the last one, We have 0, 0, 0, and then don't 1 here. And that would represent 0, 0 in binary. And you're probably wondering now, what is this Z here for? And if we look back, basically the Z, what it means is if we have, because we know there can be all other alternatives in this coding statement here, where we could just have zeros for all of them, let's say. And then there's no significant bit in here because they're all 0. So then this would be when Z would be 0 here. And the rest would then just be Z equals 1 because there is a significant bit actually located in this encoder. So the Z is just in case that there's not a significant bit because there's no 1 in here. So that's what it accounts for, as you can see in this code right here. And so for these ones, we would just have unknown. So we could just say 0, 0. We wouldn't know what those would be. And so looking at this behavior of priority, what we have here is we have a process statement and it's going to go through. So again, the most significant bit, it would be W3. The next most significant would be W2, W1, and then W0. His most significant bit is on the very left, and then the least significant bit is on the very right, which is W0. So this would be the least significant bit here. And if W3 is equal to 1, then it's going to represent that in binary form. W2 is equal 1, represents on binary form, and then continues to do that. And then finally, it's going to check and it's going to assign Z to 0 if there's no significant bit in here, if it's all 0, 0, 0. Else Z is going to be equal to 1 because the significant bit was found. And then that will end our behavior. Okay, now priority encoder, there's another version here. Goes through the exact same process. You can use either one. I'm fine with he's two, but I found this one more simple to explain. Okay, now we'll go to slide number 5. And for this one, we're going to be talking a little about case statements. And so case statements are like, when it's this, then when S is this value, then do this. So you use like the variable like S in when S is 0, and then when others would be like when S would then be 1, because it's only standard logic. It's either 0, 1. So we declare our libraries, we declare our entity here, then we declare architecture. And we begin the architecture. We don't have any internal signals or components that come beforehand. So we just start the behavior. For a process, what we do is we want to know the variables that might change the output. So our variables that might change the output are W0, W1, and S. They're all the input variables that can influence the output. And so here we just have a multiplexer, that's why. And we have a W0, and we have a W1, and then we have a select. And then we have F as our output. And so it will go through all these. So the case of S is when it's 0, it's going to assign F to W0. And when it is 1, it's going to assign F to then W1 would be the only other alternative. And so that's where it will go through. So for the select process, if it's 0, F will be W0. If it's 1, F will be W1. And so for this case, we can use case S is, so when it's 0, it's going to be F is W0, or when others, F is W1. Okay, now that we talked about that, let's get into the other parts. So 2 to 4 decoder here. Remember, decoders have an enable pin, special little nuance about them. And what we do for decoders is that we are going to discuss about how we can represent this in code with case statements. And so exact same thing that we talked about before, all the port here, we know how to do this. The only difference is here, if enable equals 1, so that means it's actually decoding, then what's going to happen is case W. So W is the inputs. So when W is 0, 0, when it's 0, 1, 1, 0, and the others would be when it's 1, 1, then do these specific, it's going to say when W is 0, 0, then for Y, assign it 1, 0, 0, 0. So when this arrow here, do not think of this as an assign arrow. Think of it as a then do this. So when W is 0, 1, then Y, assign it 0, 1, 0, 0. And so then that's what we're going to do here. And that's how you carry it out. Then you end the case, and then you go out of that. And for the next one, for the VCD to 7 segment display, what we need to do here is basically we have to match up all the specific values. So what we do is we say similar case scenario where we have a process statement and it's based off the input that's going to change the output. So that's our one signal variable here. It's going to influence the output. So then we begin the process and we have the case statement. So the binary encoded decimal. So when it's 0, 0, 0, 0 for the W pin here, then it's going to give the specific value for A through G. So how to light up the 7 segment display here. And so when it's 0, 0, 0, then assign this number to LEDs. And when it's 0, 0, 0, 1, then assign this value to LEDs. And you do that all the way down. And then when others, you can just assign it 0, 0, 0, 0, 0, 0 if you want. Then you end the case, end the process, and end the behavior. So you sort of walk out of it. And there we go. That's everything for then. Combinational circuits. The output is a function of the present inputs. Sequential circuits. This is where we're going to get on. Sequential circuits depend on the present inputs and past inputs. And so examples of these that depend on the present and past are latches, flip-flops, and registers. So combinations only depend on the present, which is super nice. You don't have to store anything. Sequential have actual memory in them. So that's where we're going to get into our D flip-flops and everything. And you'll notice we're going to use registers. So latch, the problem with the latch is the latch. Let me increase the font here. The latch, as Dr. Koo said, it can change multiple times throughout the period. So we use a flip-flop because a flip-flop relies on the clock signal, clock edge to change. And then a register is combination, basically a combination of multiple flip-flops. And so that's how you can find it out. So that's the difference between the three. And let's see how those work. And so here's a gated D latch here. And basically, if we look at these specific values, is how I remember it is just here, D clock, Q output, and then the opposite of Q as another output. So this is going to be, we can say here the present Q. Present Q. We usually represent this just QT, and then here would be the past Q if they want to say. So what we say is like, oh, the present input is a function of the past one stored. And usually we write this as Q of T just up here instead. Then we write this as Q of T minus 1, so it makes more sense with present and past. And then what we're looking at right here is the reason he didn't like the gated D latch, because the D latch, Q just follows the value D. And so if you look here, what's going to happen basically is for this D latch, if you see whenever the clock is 1, Q follows the value of D. And so we can just reference it here. You can see when D is 0, the output's 0. When D is 1, the output's 1. And then when the clock is 0, that means that D, it's not going to follow it. It's just going to base it off the past input. So what it was at that time. And so we can see here when the clock is 0, it's just going to, our initial value for Q, let's say, was 0. But when the clock is actually 1, it's going to copy the value that D has. So here it copies the value D. Then the clock went 0. So whatever value D was on, it's just going to stay on. Then the clock went up to 1. So when the clock went up to 1, it's going to start copying the value that D's graph has just here. And then the clock went to 0. So it's going to keep the same value that it had stored. And then the clock went to 1 here. And it's going to copy then the value D. So it's going to go here. And then the clock went to 0. So then it's just going to keep that same input. Then the clock went to 1 here. It's going to then start copying the value D here. So it's going to go up here, just like D, and then it went to 0. And so then it's going to keep the past input of Q. And now we're going to go down. This was the code for the D latch. It was very simple. You have your entity here. You have your 2 ports. So you have D and clock, and then you have the output Q. The behavior of the latch is, and we use the process statement here. So the only thing that affects the D latch output, if you think about it, is either the clock or the value of D. And so we start beginning, and if clock is equal to 1, then Q is going to be equal to D, and if, and then end process. And basically it will just store the same value for Q, as you notice, because if the clock is 0, then it's just going to remain at that same value that it had when the clock went 0 for D. Okay, now that we went over that, we're going to go over the next ones, which will be about actual flip-flops. So let's get into slide 6. So the flip-flop, basically for the flip-flop, how this works is we have 2 flip-flops here. And what I like to do is I just like memorizing it this way instead of looking at those diagrams of the master and the slave flip-flop. Negative edge trigger just has the bubble here. Positive edge trigger doesn't have the bubble. That's all you need to know. And so how a D flip-flop works is basically on the clock signal. That's the only thing that will affect the output if it occurs. So we can see right here for a D flip-flop, the main difference, we notice we still have D and clock as our inputs, Q as our output in the entity section. So nothing changed here, but the behavior, it's only dependent on the clock. D does not affect the output. So that was interesting because if we go back, let's see. Let me try pulling them up side by side so you can have a better view of it. So if we look at VHDL number 5 here, we look at the output here. We had D in the process statement, but here for the flip-flop, we only have the clock because the clock only determines when we want to make a change, not D. And so what we do here is if the clock has a change in the signal, so that means if it goes like either up or it goes down. So if it's a positive edge trigger, so that's what the 1 means here, then Q is going to get us, we're going to assign D to Q, and then we're going to end the if, end the process, and end the behavior. And so it's only if we have a positive edge trigger is what this statement is saying right here. So if the clock changes and it's a positive edge, then we're going to assign it. And the reason we did positive edge was because here we did not have a bubble. There's a bubble, we would then have to make this clock equal 0 because that would say if the clock changes and it's a negative edge trigger. Okay, now that we went over that, we're going to do alternate code. And so for the alternate code, oh, don't use it, he said. It's not a good practice to use. Okay, so D flip-flop.
All right, got it.
Yeah, D flip-flop with clear and preset. Clear and preset are active low. And so you can tell that by the bubble here, that means active low and indicated by that bubble mark. And Q equals 1 when preset equals 0, and Q equals 0 when clear equals 0. And so you can tell no effects when they're equal to 1 since they're active low. And so they both cannot be low at the same time, and they are asynchronous. And so that means asynchronous has higher priority. It's sort of like the king on top over the knights. They preset and clear the flip-flop regardless of the value of the clock. So it does not depend on the clock. Like the value D does depend on the clock signal. Okay, now that we know that, we're going to do the D flip-flop with asynchronous reset. And for this, we're going to have our values. And so let me pull up the one so you can see it right next to it. So I'm going to copy this over. Oh, maybe I can do it right here very easily. Okay, so for asynchronous reset, we have the picture right here, the image. Let me zoom a little out. Okay, so we have our simple libraries. We have our entity flip-flop is, then we have D coming in, we have preset coming in, clear coming in, and clock coming in. And then what we have, it looks like here they just had reset. They didn't use clear in this one because they just wanted asynchronous reset. And then for Q as their output they have here, and their N flip-flop. So then we end the entity. So I'm going to draw an image of what this looks like for actual flip-flop because it's a little different than the diagram here on the right. So we're going to have D here as one of our inputs. We're going to have reset N, which is going to be asynchronous, and it's going to be also active low. So then we're going to have to draw a circle here for active low to represent that. And then we're going to have our clock as another input to this latch, so clock. And then we're going to have Q as our output here. So Q is going to be the output terminal. And then we're going to have the behavior of this flip-flop is going to be, so we can call this flip-flop if we want, this little diagram we made here. And how this is going to behave is basically we're going to go through a process statement. So if these asynchronous signals occur, so if reset is triggered or clock is, there's a change in either one of these signal variables, it's going to, if reset's equal to 0, then the output's going to be equal to 0 because it's clearing. And if the clock changes, so it's either changing positively or negatively, and this says it's a positive edge triggered, so it's going to be this one. If that happens, then set Q equal to D, and then end the if, end the process, and end the behavior. Okay, so that's everything we have there. Oh, no, I did not want to save that. Okay, go down. T flip-flop. T flip-flop, don't memorize this diagram here on the left, just memorize this, how it looks. Same thing like a D flip-flop. All you need to do is put a T instead of a D. And basically it toggles. So we know toggle means it just flips the output. So at the active clock edge, so basically it just flips the value of what it had formerly stored in it. So you can see here at the active clock edge, when T, it was equal to 1. So it flipped it from 0 here to 1. And then here at the next clock edge for the positive edge triggered, it had for the actual value, T was 0, so it did not flip it. Here at this active clock edge, T was 1, so it flipped the value from 1 to 0. And then at this active edge, it then saw T was 1, so it flipped it from 0 to 1 here. So it went from 0 to 1. So T just toggles, so it flips the output. And then we have here registers can store, a flip-flop can only store 1 bit of information. N flip-flops store N bits of information. That's what we call a register. A 4-bit shift register basically means we're going to have an input to the very left, but then all the others are shifting over the output to the next one. So shift, shift, shift. So it's going to shift the output from the first one over to the second, shift from the second to the third, and shift the output from the third to the fourth. And so at each active clock edge, content is shifted 1 position to the right, and they're loaded in a serial fashion. using the serial input. So you're going to either have like a value of 1 or 0 here to just insert. So it keeps shifting it down the line. It reminds me of a conveyor belt. You just put it on the next one. Okay, now that I talked about that, so registers can store n bits of information using n flip-flops. And so for this one right here, what we have is we're going to have a non-shifting. So let's see how this works, because if it's non-shifting, we want to sort of see, is this going to be like a parallel one, or how's it going to work? So for a non-shifting register, we have the two libraries as always. We have our entity and our end statement. And so it looks like we have, because they called this D, looks like they have 7 D inputs. They have a reset, a clock, and they have a Q output. They have 7 Q outputs. So it looks like we are going to have sort of like 7 D flip-flops, I'm thinking. And then they have the behavior register is, so when there's a change in the clock or reset n, it's going to occur. So remember, asynchronous takes the most. It has the highest priority, so that's why it's listed first. So there's a change in the clock, and the clock is 1, so it's positive edge triggered. Then assign Q to D, and it looks like, okay, this is non-shifting, so it's just working as a normal type of flip-flop is what I'm getting from this code. Because if it's not resetting, and if the clock is positive edge triggered, it looks like we're just going to set the value, the output, to the value of D. And so that looks like if Q7 is going to be set equal to D7. And so that's basically what this 8-bit register is looking like. So let me draw it out a little just so you can see what it sort of looks like. So we just have a D7. We have a, let me just do the quick text. So we have D7 here. We have a D6. We have a D5. We have a D4. We have a D3. We have D2, we have a D1, we have a D0. And then we have also reset in n in a clock as our input. So I'm just gonna have the reset n and the clock as our inputs. And then we also have Q7, Q6, Q5, Q4, Q3, Q2, and Q1, and finally Q0. Okay, so those are all of our inputs, all of our outputs, and it just looks like literally what's happening if reset is equal to 0. So that would be active low, we know. It would then cause all these outputs to be 0. So if this is active low, then it's going to cause all these here to be 0. It's going to go through. And if the clock is actually positive edge triggered, it's going to actually assign D7 to Q7, D6 to Q6. So it's actually going to just input those as a normal flip-flop. Okay, now that we've done that, we basically talked about that non-shifting. This is just if you want to use a generic variable here in the entity, you're going to give the name of your integer, and you're going to have to say then if you want to do as many as you want for an n-bit register, you just have to do n-1, n-1 here. And then you also have to assign all the others to 0 here for reset. This is how many bits, it doesn't matter. It's just going to assign 0 to all of them. And then when it's a positive edge triggered. So it's the exact same code. It's just for an n-bit register. So say you want like 500 of these flip-flops. And so then you would put in here instead of 16, 500. And so it would go from 499 down to 0 because that's 500 in total, because 0 to 499 is 500 values. And then for reset, you'd have to set all those bits equal to 0. Okay, and that's basically how that would work. Now we're going to go up to number 7, which is going to talk a little about the parallel access shift register. So this one, in order to understand parallel loading, you're going to have to see how this works. And so we'll run through it a little because this one's pretty important, I feel like, compared
He's
to the
gonna
rest.
test us on this.
I just have like a feeling that like we need to know how this works. At least we can reference it.
Okay.
So for the serial input, usually that's just serial. For shifting and loading, I know we represent that with an L. Parallel inputs, usually like a P and a clock. It's just a clock usually. Okay, and so let's run through scenarios. Let's just set our serial input to 0 for now. So 0. Let's do shift. Let's do loading so you can understand. Loading parallel input. We have 4 of these because we have a P0 here. If you look at P0, you have a P1 here. Or wait, sorry, this would be P3, P2 highest then to lowest. Then you'd have P1 here. And you have a P0 here. Okay, so basically how you would understand this is if we're on loading mode, so I'm gonna then say for parallel input, let's just say 0, 0, 0, 1 is what we want to load in if we need to. And then our clock, basically what's gonna happen is let's draw this out. And so for drawing out, we're gonna load. So right here, this input is going to be 1. The serial input, we're just going to put as 0. And so if we do 1, not of that would be 0 here. So 0 not with 0, this gate would turn up false here. And then this one right here, we have a 0 for parallel inputting, but we have a load right here. So this would be a 0 here. So then this would be a 0. And so we get a 0 for our Q3. That matches our 0 here. Next one, if we, for P2, we wanted 1 to input in here. So we put in 1, and then our shift loading, that will be a 1 right here. So we have a 1 and a 1. And so then that would be a 1. Here we would then, let's see. This one is connected to this 0 over here. It comes from the shifting, and the shifting, since it's 0 right here, we know it's going to give a 0 and AND gate. So 0 and 1, it's actually going to produce a 1. And so this will be a 1, which matches here. Then for P1, we wanted 1. And so we had 1 inputted. And so 1 here with the loading, we are performing loading. The other one was shifting, so that would be a 0 here. And right here, it's going to be a, it wouldn't matter because it's an AND gate, so 0 with 1. Then XOR, that's going to be 1. And here it's going to be 1, so then the output would be 1. And so that's matches are 1. Here P0 is going to be 0 because we had it here marked. And so 0 with 1 is going to be 0 because right here we had a 1. And then this one would be 0, so it won't matter the other values since it would be 0 for an AND gate. 0 or XORed with 0, 0, 0 here, and then we get a 0. So 0, 1, 1, 0 is our output here. And if you look, that matches exactly our parallel input. So parallel input works here. Now we're going to do shifting. So shifting, if we have the value here, our serial input will keep it 0, but we're going to do, let's actually do 1 for serial input. I want to try that out. And then let's do for shifting, we would do 0 because the not of that, it's active low. So then that would take place and the loading would not occur because that would be a 0. And so for each of these gates here, this one's not going to occur since there's a 0 here. It's connected to this one. This one's not going to occur since there's a 0 here. This one's not going to occur since there's a 0. And this one's not going to occur since there's a 0. And so all these right here are now going to be having 1s inputted for them. So because we're now doing shifting. And so when we inverse the 0 coming in, because this was where our 0 was, it's going to produce a 1 here, a 1 here, and a 1 here, and a 1 here. So now we need to look back at the outputs that we had actually stored. So our serial in, we had a 1 value. So for this one, it's going to produce a 1 here, which will produce a 1. And 1 XORed of 0 will be 1. And so this would be 1. And this one over here to the right of it, it's going to implement. So if we had 1 in Q3, 1, 1 will produce 1. And then because there'd be a 1 here, so 1, and then this one would be 0 because it's not active to state. So I'll produce 1, so we get a 1 here. And then if we look here for next shift, it's going to actually go through and it's going to implement it. So if we look through here, shifting's 1 and our new output would be then 1. And so then it's going to go through and this would be 1, while the other one would be 0. 1 would go through here and then this would be 1. So we get 1 here. And then if we shift again at the next clock cycle, this one would have a 1 in here. 1 with 1 would be 1. And so then this would be 1. And then this output here would be 1. And so it shifted the value each time. So it was able to implement in all ones across for the shift value over the clock cycles, is that each new cycle, this one would change then from the value it had stored in the parallel input. So it would start going. But how this would occur at first is because we formerly had 0, 1, 1, 0. And for our serial input, we had 1. And so that value is going to go in this. This one's going to go over to the right. This one's going to go over to the right. And this one's going to go over to the right. The next clock cycle, this serial input is going to stay at 1. So it's going to go here. Then that value over here from that red one's going to go over here. From this red output, it's going to go over here. So it's going to keep shifting to the right. And so it's going to shift, 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 shift at each clock cycle. And so that's one important thing to take away. And now that we've done that, we talked to Lou about this already. For a 4-bit shift register, he created structural coding for this. So he just declared, as you can see here in the diagram, is use the libraries, use the entity, called it shift4, had the, he used R for parallel inputs here. I used P, I find that more better. L for loading and shifting. W, he used here for the serial input. And then the clock here, he called it clock. And then for Q, those were the outputs. And because they're used as outputs and inputs, if using the serial function, then he used buffer. You can also say in out, whichever one you want to. He used the component. So he was able to represent this using a mux differential. And he created 4 of these components here. So 1, 2, 3, 4. You can see he instantiated it 4 times right here. And for that component, he had D0 enter, had a D1, a select, a clock, and a Q. And so he told us that he used that 4 times. It was just a simple multiplexer and with a D flip-flop connected to it. And so that's what he did. And after that, he did all the port maps and ended the structure. And so that's for the 4-bit register. There's behavioral coding for this. Behavioral would just be using the specific values we have for the equations or truth table, what we could think. I sort of like behavioral for this. I thought it was easier to understand because for parallel loading for the clock and for the LW for the loading and for the value of the serial input and for Q, what he did is for the process, you begin and instead here, he uses if clock event and clock equals 1, so positive edge trigger. And if the latch is equal to 1, so we need another end if here because we created an if statement. So if the latch is equal to 1, so loading is equal to 1, then you need to start the value that you input for the load is going to equal the value output. Else, then we're going to do shifting. So this would be, okay, the value for Q0 is going to get the value from Q1, Q1 is going to get the value from Q2, Q2 is going to get the value from Q3, Q3 is going to get that serial input. And so that's all the shifting. So this is parallel loading here. And here's our shifting down here. And that was basically how the behavioral code worked. I thought it was a simpler example. And then he just showed you with an n-bit register how you could do it. And that was pretty much it. Now we'll talk about the asynchronous ripple counters. And so how he got these specific counter values is he created a truth table here. And so let's see how this truth table works. And so for the asynchronous ripple counter, let me create. So I'm going to have. Okay. What we need to do is we notice our value for clock Q is our output. So we have Q0 here, or Q0, Q1, and Q2. And then we have to determine how this should be hooked up into in order to produce this timing diagram here. And so in order to produce this timing diagram, we're gonna run through truth table and show you how it works. So let me just pull this up to make sure I do it correctly in the truth table so we don't accidentally make any mistakes with the truth table counting. And so looking at this, how he designed it, he said for our count table, we're gonna have, okay, Q2 and then Q1 and Q0 and let's see, Q2, Q1 and Q0. And then for output, we're going to say, this is just going to be the count, so we know which count we're on. And you can see we're going to have, it's a 3-bit up counter. We can also say modulo 8. And you can say also, instead of modulo 8, you can reference it as a count up to 7. So count 7. So you can say 3 different things. The reason why it's modulo 8 is just because if you think about it, counts from 0 to 7, that's 8 specific numbers you have to go through. And so for our values here, we're going to have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Okay, so that's all of our possible outputs we can get here, so you guys know. Let me space these out because we're going to show connections between the two. Okay, let me. And for a count now, we're going to have to say which variable we're counting on. So we're going to go from 0, 1, 2, 3, 4, 5, 6, 7. Okay, that's our count. And now what we need to do is we need to show how it counts. So we're going to show that through here. So Q0, it looks like it's changing every single one. So if it's changing every single one, that sort of mimics the clock. So it should just mimic the clock because the clock changes every single one. And so if we see, we hook the clock up to the actual clock signal for this Q0. Now let's look at Q1. Q1 changes when right here from 0 to 1 and changes 1 to 0 and changes 0 to 1. Looking from here, that's when Q0 goes 1 to 0, 1 to 0, and a 1 to 0. So Q1 changes when Q0 goes from 1 to 0. However, it's a positive edge triggered. So that's why we just say Q naught 0 goes from 0 to 1. So let me draw that little above because it's a positive edge triggered right here. You can see there's no bubble to make it negative edge triggered. We have to connect it from Q naught 0 because that's when it goes from 0 to 1. That'd be a positive edge triggered. And so that's when we do it there. And then for our Q2, we notice it changes here when Q1 goes from 1 to 0. And that's the only time when Q1 goes 1 to 0. So what we can write here is we can write, I'll just write it over here because I'm running out of room. Q2 changes when Q1 goes from 1 to 0. That's the exact same thing as saying Q1 naught goes from 0 to 1, which is positive edge triggered. Q1 bar, sorry, because that'll be the opposite. So that's why we hook up Q1 bar here because it's a positive edge triggered, and that's when Q2 changes. And so that's when it would toggle. And so that's how we can create this asynchronous ripple counter. Pretty cool. Okay. Now we have a down counter. So down counter done me exactly the opposite way. Man, I'm just like, oh, have to write all that out again. Okay, so for the down counter, basically what happens is we have a Q2, we have a Q1, and we have a Q0. We're counting down. So in order to count down, we're gonna have 1, 1, 1. We're gonna have 1,
Oh,
1.
sorry that I phased out for a little bit, my internet connection.
Oh, you're good. 1, 0, 1. We're going backwards here because we're counting down. So 0, 1, 1, 0, 1, 0, 0, 0, 1, and 0, 0, 0. And so that's basically how we have it here. And then counting. So for the count, remember it's count down. So we're going to go from 7, 6, 5, 4, 3, 2, 1, 0. Okay, now we're going to be heading downwards. And so Q0 is going to change if we look at it every single time. So it's changing all the time. So we're going to just hook it up to the clock. And here, when we have it hooked up to the clock, oh, oops, edit redo. Okay, let me just put that back in. So that's why we have here, clock is hooked up to Q0 here because it's changing every single time we notice, just like the clock changes every single time. Now we're going to go to look at Q1 here. So if we look at Q1, Q1, it changes when, look right here, 1 to 0, 0 to 1, 1 to 0. And that's when we have Q0 goes from 0 to 1. Q0 goes from 0 to 1. Q0 goes from 0 to 1. And so Q1 changes when Q0 goes from 0 to 1. And it's a positive edge triggered. So that's good because it goes 0 to 1. That's positive edge. So we just hook up Q0 to 0 over here. And that's how we get that value. And then our next one we have to do is we're going to talk about Q2 when it changes. Q2 changes here from 1 to 0. And if we look here, that's when this one, the only time it goes 0 to 1. And so Q2, we can write here, changes when Q1 goes from 0 to 1. Okay, so that's when all these occur. And we looked at it and now we feel pretty good on those. And so that's why we have these specific ones hooked up, these clocks here. For Q1, it changes when Q0 goes from 0 to 1, and Q2 here changes when Q1 goes from 0 to 1. So that's why we have it hooked up for these clock inputs, because it will always toggle then when that clock is positive edge triggered. Okay, now that we know that, let's go to finally the VHDL8, which was a synchronous up counter here. So synchronous, the reason we use it over asynchronous was there was two main priorities. We noticed back in our asynchronous, there was a little of a delay time. And because of the delay, that caused us to not want to use it, because if there's a delay, it's going to cause there to be a little bit of an error on there. And so it's going to delay each stage. Where synchronous counter will clock all the flip-flops at the same time. And you just need to determine the T input connection here. And so what we have here when we're looking at this for synchronous up counter is we have these outputs. We have the clock connected to each of these T flip-flops, which is different from the last one we had. So we have it connected to all of these, and we have 4 of these flip-flops. So that means we're going to count up to 15, so 0 to 15. And when I'm looking at this, I notice the output Q0, and then it's ANDed with Q1. Let's see why here. And so it's a little bit of a different. So we're going to make our truth table. And we're going to have our truth table have Q3, Q2, Q1, and Q0. And then those are all of our inputs here. And then our count, actually, we need to take into account. So we're going to go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, I don't know if I can fit that. Let me see. Let me try decreasing it to around 14. 11, 12, 13, 14, 15. Okay, and then for values, I'm just gonna actually just make them here. So it's up counting, so it's gonna go here between, let me try making these a little more space. Let me do 0, 0. Okay, there we go. So we finally got all those specifics noted. And so when we look at Q0, we notice it changes every single time. It goes 0, 1, 0, 1, 0, 1. So that's basically on the clock. We can hook it up here. So that makes sense why we have this hooked up to clock. And because Q0 is going to change every single time. So we will toggle every time the clock is positive. And then for the next one, for Q0, what we need to do is we need to determine Q1, when is it going to change? And if we notice, Q1 changes here, 0 to 1, 1 to 0, and then goes 0 to 1, 1 to 0, and 0 to 1, and 1 to 0, and goes 0 to 1. Okay, so if we're looking at this, that occurs always basically, let me take a better look just to make sure I get that correct.
is for that synchronous up counter, it occurs whenever we notice Q0 is equal to 1. So if we look, Q0 is equal to 1 here, 1 here, 1 here, 1 here, 1, and so that change is always occurring when Q0 is equal to 1. And so that's the important takeaway here, is when we see that, that is pretty significant, because we're like, okay, when Q0 is equal to 1, then that's going to be our new T here, because that's when it changes. Now we need to look at the next one, which is Q2 for that input for the T. So if we look at Q2 here, it changes right here. It changes right here. Changes right here. And so we notice it changes when we have 1, 1 for both of these. Changes, look, when these are both 1, 1, and changes here when these are both 1, 1. And so we need Q0 and Q1 here. When they're both 1, 1, this AND gate will turn true, and that will toggle the value Q2. Okay, now our next one is when Q3 changes from 0 to 1 here. That's going to be when all these are 1, we notice. So that's why we have this AND gate, which is the combination of Q1 and Q2. The combination of Q1 and Q0 ANDed with Q2. So when all these are 1, it's going to toggle the value Q3. Okay. So now we know the synchronous counter with enable and clear. Basically, enable just means the counting stops here. It will stop it from happening. Since enable drives this input, so it will cause it to be 0. Because in this other one, we just saw it's connected to 1. But in this one right here, the enable will stop the counting because it will just make this 0, so it never toggles. And then if it's to 1, it will produce normal counting. Okay. And when we put in clear here, all the flip-flops outputs are 0. Okay, and basically he just had this using a D flip-flop. So he just said, oh, in exchange for T, what he said is the T flip-flop, he used this instead for D flip-flop. So if he says construct a 4-bit counter using a D flip-flop, this would be what we need to reference here. And now let's go to the next. With parallel loading capacity, the only difference here is he added in this multiplexer, so it could put in the load values in case we didn't want to do up or down counting. He just wanted to input the parallel load values. That's why you put these multiplexers in here. So we just insert the values we want for these parallel loading. So it just is the parallel loading right here. And what that does is when this is 1 for the select, it's going to perform parallel loading and just put D0 as Q0, D1 as Q1, D2 as Q2, D3 as Q3. And the other mode, if it's not, it would be then counting upwards. Okay. Now that we talked about that, this is the 4-bit up counter code. And so this one's not too bad, luckily. It's just a library. So we need to use an up count, the ports. We have a clock, we have a reset, and we have an enable pin. And we have an output for Q. So the behavior of up count is we have our internal signal here, the begin, the process of the clock, and the reset. So these asynchronous and the other one, which is synchronous, but it will determine a change in the output. If reset 0, then the count's going to be equal to 0. Else if the clock is a positive edge trigger here, then if enable equals 1, we're going to add 1. If enable, that means is 0. If that's not true, then just keep the count the same, counting stopped. And then end the if statement, end the if, end the process. Finally, assign Q to the count. Another way you could do this instead is you could just make Q as an in out. And if you have it as an in out, you wouldn't need this right here. And instead of count, you could just put Q here. And you could put Q here, and then you could put Q here, Q here, and Q here. Okay, and then you wouldn't need the statement. but that's just a nice little trick. Okay, now that we've done that and we done this one's for parallel loading. So the difference here, same libraries. We declare one for our parallel input. So what we're going to input, loading, and this is our clock, our reset, and then our Q output. Then we begin. Here's our 2. Reset is asynchronous. Clock is our synchronous coming in. If resets equals 0, then the outputs are all going to be 0. If the clock is positive edge trigger here and it occurs, the in loading is set to 1, then do parallel loading. Else, it's going to be counting. And then end the if and the process and the behavior. Okay. And let me see. Now we're going to get into 8A. 8A is a modulo 6 counter with synchronous.
Okay, Brian. This okay. After this, I have to go, but I really appreciate you for like going over everything.
Yeah. Okay. Yeah. This one, I know it's getting late, so I'm gonna have to go too. My voice is killing me right now. Okay.
Yeah. So you'll post this up later.
Yeah. I'll just put it on YouTube. If that's
okay. Then yeah, just give us the link to it later.
Okay. The modulo 6 counter. Basically, what it does, it's a non-modulo 2 to the n counter because it only counts up to a certain number. Like, remember how we talked about binary, like 2 to the first, 2 to the second, 2 to the third. That counts up to, if we think about it, 2 to the first, that would count up to 1 because 0, 1. There's 2 numbers in there. 2 to the second would count up to 3. 0, 1, 2, 3. There's 4 numbers in there. 2 to the 2 to the third, which counts up to 7 because 0, 1, 2, 3, 4, 5, 6, 7. There's 8 numbers in there. And what this does is a modulo 6 counter. There's no counter to count up to 6. So this is a non-modulo counter is what we referred to it as. And that's a pretty important part. He wants us to know that as well. And for this non-modulo counter, it's what we need to do is he does not want us to not use the counter with a synchronous reset. And he wants us to use the counter with asynchronous reset. And use, oh, sorry. Use the synchronous. Sorry, I got those mixed up. Use the synchronous one. The reason why we don't use asynchronous is because asynchronous does not wait for the clock signal, and that's the issue with it. And so what we look here is we know the load is equal to Q2 times Q3 here. Times Q3. And we Q0 times Q3. Okay. 0 times Q3. And that's pretty important. And so now that we know, oh, where am I getting this Q3 from? Q0 times Q2. Okay, so we know that as our load. And this enable will keep counting. That's what it does. Is so enable set to 1. These right here are parallel inputs right here. And so let me put that in text, parallel input. And then we have basically what happens then is at that load, if you think of our count table, sort of, just go back to it real quick. Remember how we counted and we talked about it? And I was like, oh yeah, so you remember we go like 0, 1, 2, 3, 4, 5. And if we want to reset at 6, and if you want to think about the outputs Q2, Q1, Q0, and that's going to go from 0, 0, 0 for the first count, 0, 0, 1, 0, 1, 0. Okay, and so the important part here is when we want to reset it is it counts then up to 5 because modulo 6 means count up to 5. And like we discussed earlier, there's other names you can say for it. Count up to 5. You can also say a certain n bit counter. So what we have here is if we want to count up to 5, then we want to stop after. So these are when we need to reset it right here. So when we have Q0 times Q2, why didn't we include times Q1? The reason we didn't is because this is the only time Q2 and Q0 are equal to 1. That's the only time that it occurs in all these inputs. So we can just simplify it. Instead of saying Q0 times Q1 times Q2, we can say Q0 times Q2. And then we reset it when that happens. So when we load that in, so when those are equal, then what's going to happen is it's going to, as we can tell right here at 5, it's going to, at that clock edge, we have 1, 0, 1. It's going to reset it to 0, 0, 0. And that's how it will happen. So the synchronous reset will occur at that clock edge. And that's the important part to take away from this. The asynchronous, it has a short duration through sort of 6. That's why we don't like it, is because it's dependent upon that clock. With the asynchronous reset, it does not wait for that clock signal to occur, so it messes it up. So only use the basically synchronous reset for a non-modulo counter. Okay, for a ring counter, what you need to do is, a ring counter is not a real counter. It's a shift register D flip-flop. And so what happens is it sort of has like a ring structure. He didn't really get into this, so I don't think you need to know it. Okay, for the next one, this is, if you look at it, it does anding, then oring. And if we think of that, doesn't that remind you of sum of products? Because first we and them for the product, then we or them together for the sum. And so this is a general structure of a programmable logic array. It has programmable switches in these planes. And then if we go into the programmable array down here, what happens is you notice in this one, wherever, let me go to this, wherever there's an X, that means there's a connection here. So P1 is going to be equal to X1 times X2, because this is in the and plane. P2 is going to be equal to X1 times X3 naught. I'm just going to symbolize that with exclamation mark in front. P3 will be equal to X1 naught times X2 naught times X3 naught, or sorry, just X3. P4 will be equal to X1 times X3. And then we're going to OR these. So what's going to happen here is when we OR these, it's going to do the ORs down here. So it's going to do, man, sorry, those outputs are going to get a little shifted. But F right here, let me just draw it. F1 is going to be equal to P1 plus P2 plus P3 from up here, because that's where it hits the connection. And this F2 is going to be equal to P1 plus P3 plus P4. Okay, and now we know those connections. And then what we can do up here, it's basically almost the same thing we have right up here. Just instead of them having the X, they just had a fuse where they just had it disconnected here for their programmable connections. So they just didn't have X markings, but it's the exact same way. You could just whichever one was connected, you're good. So now we're going to talk a little about the programmable array logic. And these are different because they only have an and plane. They don't have an or plane. And so the or plane is fixed and it's cheaper. And that's what causes this one. So that's the only difference. I won't get into many details about that. And now we're going to get into this is what it looks like. So we know the programmable array logic. It just has inputs, outputs, interconnection wires between them. And what you just need to know is for the FPGA, it doesn't contain and or planes. It contains logic blocks, interconnections, input, output blocks. Logic block can be a lookup table or a D flip-flop. And so basically what we have here is our lookup tables here. And then we have a 3 input lookup table. And this is how our FPGA board would work. And what you do is you just connect those right inside of it for the actual interconnection wires. How you look at it, you trace it backwards, and that's how you're able to get your functions for each of them by just tracing it backwards, and then that's how it works. So I'll just conclude it there. Let me